Discover Nomadic Labs. On peut y aller? Ok, merci à tout le monde. Alors, attendez que je prépare mon... Tu peux jeter mon écran, s'il te plaît?
Can you hear me better now?
Yes, we can. Yeah, it's better. We don't see your face. Yes, like this, perfect. Là, c'est slide. Là, c'est slide 1 minute. Oui, mon écran 1 minute et après zoom sur Adrien. At least I guess everyone get the sound, so I can start. So, bonjour à tous ici à Paris. The day will be in English because we have hopefully quite a few people on the YouTube live stream. I guess the link has been published somewhere, Twitter or something like that. So with whomever could be interested. My name is Michel Moni. Yeah, you have my screen. So we have Roland, Adrien on Zoom. Let me put this full screen. So my name is Michel Moni. I'm working for Nomadic Labs in Paris. I'm also a board member of the Tezos Foundation. So it's a real pleasure for me to host you to this Developers Day. So we took the opportunity of having HSCC this week to have this day running at Maison de la Mutualité. We didn't plan the COVID-19 and stuff like this, so the organization has been a bit shaky. I hope you will apologize the imperfection and you will still appreciate the day. The program is like this, so exactly as it's been published on the Nomadic Labs webpage. So I'll make the welcome as short as possible. We are running a little bit late. We will start with Adrien Brink, who is working for Cryptium Labs in Zug. Adrien couldn't come for the reason that we all know now. After that, we'll have Christian and Rémi Le Sénéchal, who will be live from Paris, so we'll be here. And we'll terminate this morning session with a kind of lightning presentations by 5 companies who are using Tezos. So let me introduce Adrien now. So maybe you could switch the camera to the Zoom. Adrien, it's up to you. You have between 30 and 45 minutes, so do as you want. Thank you.
Okay, cool. Thank you very much, Michel. Can everyone hear me? Thumbs up? Okay, perfect. In that case, I will quickly share my screen. I have like one slide. PowerPoint share. Does this work? PowerPoint there. Can you see my screen now?
Yes, we can see the screen.
Yes, okay, perfect. So you see the introduction slide. So thank you very much for coming to this talk. It's going to be relatively, it's novel for me as well. So this is my 3rd time doing a virtual presentation. And this is the first time doing a virtual whiteboarding session. So I actually only have 2 slides and the rest we'll do on the whiteboard. So please bear with me. I hope this works well. As a quick introduction to myself, to give you some background where I'm coming from, I'm Adrian. I'm the founder of Cryptium Labs, which you may know for Valide and Tezos for protocol development. But Cryptium Labs really is a company that is focusing on running highly secure proof-of-stake networks out of Switzerland on physical hardware. And we, as a company, run a bunch of networks that are technically interesting and novel in order to help those networks be secure and push those networks forward. Besides that, on the slide, you should be able to see also Metastate.ch, which is a research and development company that we not spun out, but that we sort of have as an umbrella company that focuses very much on bringing blockchain technology or like on solving novel problems within the blockchain space in order to tackle some of the larger looming questions that we have within the industry on how do we get this to broad adoption, how do we solve some of the fundamental challenges. Specifically, we're working on Tezos protocol upgrades. So Karthik activated yesterday, and it worked very well, very smoothly, which I'm super happy about. So this is sort of one of the core engineering principles, core protocol development. That's the first thing. Secondly, we also build, we have 2 research projects, which are, one of them is Juvix, which is a dependently typed smart contract language that should come out in sort of the next 3 to 6 months. And the last part is we are building a bunch of tooling and applications within using zero-knowledge proofs, such as a multi-asset tool, which will also release in sort of the next 3 to 6 months. This is a quick introduction into Crypto Labs, and MetaState, and myself. So thank you very much for coming to this talk about Tezos, Ethereum, and others. It's a brief overview of how Tezos works and also what the other platforms do and how Tezos compares against them and what you have to take into consideration if you're planning to build a dApp on Tezos. Cool. With that, we can stop the share and just, if you can make the video full screen, because I'll be writing on the whiteboard. Where did my pen go? There. Also, if there are questions during the talk, I'm super happy to answer them straight away. I don't know if you have a good chat room where people can ask questions. Otherwise, if there are mics, just raise your hand and you can ask me also during the talk, so we don't have to have the Q&A only at the end. And with that, let's get started. So the first question is, what is Tezos? Right? Sort of a very brief, high-level overview of what Tezos is. And I should have my notes with me here. So Tezos really is a decentralized, permissionless, and censorship-resistant public blockchain. And this is quite important because it allows you to deploy any sort of application that you can fit and run within the virtual machine that Tezos has, and no one can censor this or can stop you from deploying it. This is very different than sort of the existing computational model where you have to deploy to AWS or Google Cloud or run on your own physical hardware, but it's relatively simple to censor and stop those applications. So there's this, and the other thing, it's trustless in the sense that users can very easily check what code is actually being executed, and if that's the code that's being, if the code that's on chain is going to be the one that's executed. So there's very little room for the operators to cheat. Right, it has smart contracts, and we'll talk more about them in a little bit. And it is one of the first live, I think actually the first live proof of stake network that is actually secure in terms of proof of stake. So Tezos launched in June 2018 with the beta net, and maybe I should write some of these things down. Proof of stake. So it's proof of stake, which is a lot less wasteful than proof of work in terms of energy consumption, and also has a bunch of other interesting features where it's in proof of work, the security of your network is extrinsic to your chain, whereas in proof of stake, it's intrinsic to the chain, which means that we can build protocols that actually understand how the chain itself is secured and can sort of modify the security parameters. Due to that, it is very likely that proof of stake is probably more secure than proof of work in the long run, because we have, as a community, as the token holders of these networks, much more control over the underlying security of these chains. The second really important point about Tezos is it has governance. And again, here it's the first chain that actually launched with governance inbuilt. And when I say this, I mean Tezos is a governance process that is defined on chain. So almost all chains that launch, I just want to switch speakers. The first one is to have a governance process that's described and encoded on chain. Things like Ethereum and Bitcoin have governance, even though they sort of don't publicly say that they have a governance process. But of course, any existing system has a governance process by which people make choices on the underlying system. In Ethereum's case, it's mostly an oligopoly, where a bunch of people will come together in back rooms to make deals on how the system should evolve, which leads to, first of all, that process being very opaque and at the same time very slow. Which you can sort of see, we'll talk about this in a bit as well, but Tezos has undergone pretty much a network upgrade every 4 months that added more and more useful features to it, whereas Ethereum had 3 hard forks in its lifetime and really hasn't changed all that much from inception. Yes, so this is sort of governance. What is Tezos? Any questions on the high-level idea of what Tezos is? So it's a smart contracting platform that is decentralized, permissionless, and censorship resistant, and has a governance mechanism inbuilt. Any questions so far? Otherwise, we can move on to the next topic. Okay, I think this is okay then. So I just briefly want to talk about what else exists in the industry, right? It is very easy to become sort of very pigeonholed into a specific thing. But especially within the open source community, it's always very beneficial to learn from what others are doing to try and figure out whether you can work with those. So due to that, I'd like to spend a couple of minutes just thinking about and talking about what else exists in the industry today. So we have chains such as Bitcoin, right? Bitcoin doesn't really offer smart contracts. Its entire idea is that it's proof of work. It's a sort of most secure proof of work chain, and maybe it has the claim to become money in the future. We'll see. Then we have Ethereum, and Ethereum is somewhat similar to Tezos. Right? Ethereum also has smart contracts. It's proof of work, though. It doesn't have a governance mechanism. There is no huge sort of upgrade mechanism in place when you compare this to Tezos. Then you also have things like Cosmos and Polkadot. Which are really interoperability solutions. And whether these will be valuable or useful is yet to be determined, because we really have not yet explored the concept of interoperability within blockchains. So Cosmos really is focused on building a routing hub for messages between blockchains, and Polkadot is roughly trying to do the same, but also provide security to other systems. So these systems aren't smart contracts in that sense. And then now you start to have sort of a third wave of things which aren't live yet. So Polkadot is also not live, sorry about that. But you have things like Near and Solana and Celo, which are sort of a combination. Oh, by the way, also all of these are proof of stake. So are these. And these are sort of proof of work. But these don't have smart contracts. And Near, Solana, Celo will have smart contracts that are also proof of stake, but it's unclear how these systems will fit into the industry. All right, let's quickly erase this. Okay, so now as the third thing I'd like to talk about is really sort of a high-level comparison of Tezos and Ethereum. Right. So how do they differ? How are they similar? So we have Tezos on one hand here, and then we have Ethereum. So both of them have virtual machines, meaning that you can have smart contracts that execute on these systems. In Tezos, this is a Michelson virtual machine, and the programming language is called Michelson, and we execute Michelson contracts on chain. In Ethereum, we have the EVM. Michelson sort of took a lot of learnings from what didn't work in the EVM. Michelson is strongly typed, so it's fairly easy to do formal verification of the smart contracts that are actually being deployed to the system. So you can get very low-level guarantees that the smart contracts do what they say they do. Whereas in the Ethereum virtual machine, this is really not possible due to the fact that this is effectively sort of an incredibly low-level virtual machine over which to do formal verification is very difficult. However, as developers, most people aren't going to write their contracts in either the Ethereum bytecode or Nicholson. So we have a bunch of higher level languages. In Ethereum, this is really only Solidity. There was this try to get a language called Viper, which looked closely, was like sort of like Python, adopted. That never happened. And it sort of just fizzled out. It's still around, but no one really uses it. So in Ethereum, we only have Solidity. And believe me when I tell you that writing Solidity programs is not fun. And it's incredibly error prone, which is what we've seen so far, right? In Ethereum, even the people that built the underlying implementations for the Ethereum virtual machine in the case of Parity Ethereum wrote and deployed smart contracts to Ethereum that were so broken that they lost, I think at the time, $100 million. This is the last Parity Ethereum hack where they lost access to the sales from the dot sale. In Tezos, so it's much earlier. So we have none of these languages are sort of as battle tested as Solidity. This is one of the downsides, but we have a couple of languages actually. So we have LIGO, we have SmartPy. We also have something called Lawrence. Eventually, we'll also have something called Juvix, which I spoke about earlier, dependent types for smart contracts. So maybe this is still very early on. This is still research, so it will take a couple of months before this gets ready and is usable by the public. But LIGO is kind of nice because it has a couple of different front ends. It has Pascal LIGO and Camel LIGO right now, I think. So whatever, if you're a Pascal developer, you can easily pick this up. SmartPy is metaprogramming in Python, and Lawrence is metaprogramming in effectively Haskell. All of them compile down to Michelson, and so the contracts that you deploy are Michelson, but you don't have to write Michelson by hand, which is a huge benefit, by the way. Writing Michelson by hand is annoying because it's a stack-based language. So it's much nicer to sort of write a contract in something like LIGO. Then you get it as an output Michelson. You can look at the Michelson code yourself, formally verify if you want to, and then deploy the Michelson code to the chain. And now maybe some of these vanity metrics that people like to talk about. How many transactions a second do you have? Well, in Tezos, we roughly have 30 transactions a second. In Ethereum, we roughly have 15. The thing is, in Ethereum, this number isn't going to change, at least with Ethereum 1. This may change in a magical future world where Ethereum 2 actually works. In Tezos, it is very likely that in the next year or so, we will bump this by an order of magnitude, at the very least. This all comes down to the fact that Tezos is an active governance process and has multiple core development teams, out of which I built one of them, and the other one is Nomadic, and the third one is Dai Lambda in Japan, that are actively working on shipping useful upgrades, so every 3 to 6 months, that improve the underlying system. Right, and we talked about this a little bit. So we have security, Tezos proof of stake, Ethereum proof of work. For consensus, it's ME plus in Tezos, which is effectively Nakamoto consensus. And in Ethereum, it's also just Nakamoto consensus. Nakamoto. Again, this will change in a relatively soon in a protocol upgrade to add finality to Tezos. So that is yet to come, but it's in the works, finality, where hopefully we can get instant finality by using something like a finality gadget in order to finalize blocks. And then the last thing we have here is governance. And in Ethereum, we have an oligopoly. And in Tezos, we have coin voting. And just to explain you a little bit what coin voting actually means, it means that in Tezos, anyone can inject a proposal, so a new software upgrade that the network should upgrade to, and then the entire community of XTZ holders, and by community I really, in this case, mean XTZ holders, can vote on this upgrade. And if a supermajority of them accepts it, then the upgrade will automatically get deployed to the chain. Right. Any questions on any of these topics so far? Does any of this make sense, or am I speaking total gibberish to you that no one understands what I'm saying? There we go. Okay. I think this is probably a good sign. In this case, I quickly want to go through the architecture of Tezos. So how does Tezos actually work? Architecture of Tezos. Because it's important to understand how
just a second. It would be great that you capture the whiteboard in order to make it more visible, because the whiteboard, the way you write is not so readable. But if we have a better screenshot of the whiteboard, it would be great. Yeah.
Okay. Yes. That's actually a good point. I'll take.
Sure. I don't know. I mean.
Thank you, Adrian.
Okay. This is. I'll also try to write more cleanly. Yes. So architecture of Tezos. So how does Tezos actually work in practice? So most blockchains really have a sort of a threefold stack. You have, at the very top, you have the protocol. Then underneath that, you have a consensus mechanism. So how do nodes agree? What is the canonical chain? How do you extend that chain? And underneath of that, you have some P2P layer that exchanges messages. And these lower two parts, this distinction isn't necessarily super clean. There's some bleed between the protocol and the consensus. But generally speaking, this is part of the shell. So this is the sort of the environment that the protocol runs in. And the shell cannot be upgraded through voting on chain. However, the protocol, in the case of Tezos, is written in OCaml. And the way this works is kind of fascinating, because you have effectively what you can imagine as an abstraction layer between the shell and the protocol. So the protocol can be upgraded via on-chain upgrades, meaning that anyone in the world can write a new protocol version in OCaml, inject it to the chain, and if people agree with it, then the protocol, then the shell, the node, will automatically download the new protocol, compile it in a restricted subset of the OCaml compiler, and hot link it into the underlying shell, into the running shell. Due to this, there's almost no way to prevent from a protocol upgrade going through, right? Imagine what would happen if someone injects a protocol upgrade which removes all economic incentives, or which punishes a single validator because a single validator is behaving maliciously most of the time. And so we can't slash this automatically in the protocol, but rather we have to manually slash this. In things like Cosmos, the validator set as a whole could just refuse to upgrade. They could just stop their nodes and say, we aren't going to support this hard fork. We want to stay on the existing protocol. We ignore what governance said. In Tezos, we have binding on-chain upgrades. That means if something gets voted on in governance on-chain, every node in the network will upgrade to it. Sure, you can block this specific protocol hash, right? You can block this specific protocol hash, but then someone else tomorrow can go add one comment, changes the hash, and re-inject the protocol. And then people vote again, and eventually the system will upgrade to whatever the majority of coin holders wants. This is quite important because it makes the system very resilient against external capture of actors that don't necessarily have much stake in the system. Yes. And really the way you can the way I conceptualize this abstraction level is that you can think of the protocol as something that is sort of running in its own process and only talking over RPCs with the node. And there's sort of a very clearly defined interface between the protocol and the node. And as long as another protocol adheres to the same interface, it is compatible with this node. There's also a second type of upgrade in Tezos. What happens, because let's assume, so the shell exposes an interface to the protocol that can be used by the protocol. But for example, maybe we want to add new cryptography. Maybe we want to add BLS signatures, and we don't want to have to implement all of the cryptography within the protocol. Maybe we just want to bind to some Rust libraries and expose them through this interface. In that case, that's called an environment upgrade. And what happens here is that everyone will have to update the shell or the node in order to update the interface that this node exposes. And then the protocol can have access to all funky new functionality, such as null cryptography. This is most likely going to happen in the next upgrade, so in 007. We will try and upgrade the environment at the same time because we want to add a bunch of new cryptography to the protocol in order to support zero-knowledge proofs much better. So specifically, we're planning to add BLS signatures or BLS cryptography, exposing both the Michelson as well in the interface. Yes, and so this protocol is really, it's the rules of the game. It's the economic rules of the game. So it says, how do you create an account? How does governance work? How does slashing work? How does staking work? This blob is where I spend sort of 90% of my time in order to make it better in the future. Right, let's also very quickly talk about the proof of stake mechanism. Let me start off by saying that proof of stake is not consensus. They're two separate things. I mean, if I had slides, I could flip back to the previous slide. But proof of stake is not consensus. Proof of stake is a civil protection mechanism. It determines who is allowed to participate in the underlying consensus. Because consensus can either be something like Nakamoto consensus, so longest chain, heaviest chain, what Bitcoin is using. And then proof of work is how you select who is allowed to participate in the Nakamoto consensus instance running on the network. In Tezos, we have, for consensus, we have ME+. And this is effectively a variant of Nakamoto consensus, heaviest chain. And then we have a novel proof of stake mechanism called LPOS, liquid proof of stake, that determines who's allowed to participate in ME+. And there you have staking. So anyone with at least one role can register to become a validator on the network, or baker, as you call them in Tezos. And you need at least 8,000 XZ for this. And then you assign one role. So we measure everything in these arbitrary units of 8,000 XZ called roles, just to reduce the computational load on the nodes themselves. And so people participate in this, but let's say I only have 8,000 XZ, I sort of start my operations, but then people can delegate to me. So there's this notion that if you have, let's say, 10 XZ, you can delegate them to someone. Delegate here. Delegate to some validator. And this validator, right, there's also, in order to incentivize people participating in the security of the network, there's also sort of inflationary rewards in Tezos. So every year there's decreasing over time, since this is a fixed number. There's a 5.51% new issuance of rewards. This means, yeah, so a year, but this is going down over time because these are fixed numbers per block instead of actual percentages. 5.51 was just what happened effectively on the first block of the network. And this gets distributed to validators. And these validators, it's up to them how they want to share this reward with the people that delegate to them. Most people share 90% of those rewards back to the people that delegate to them. But most importantly, why is this actually secure? Because in proof of work, you have to make a choice which fork you mine on, right? I have to decide, do I put my ASICs to work on block A or block B? And this is a mutually exclusive choice. In proof of stake, we're only signing with cryptographic keys. I can create 10,000 signatures a second. So I could sign on all possible blocks here. But if you do this, then the network never converges to canonical history, and we sort of end up in this massive ever-growing tree where we don't have a blockchain anymore, but rather we have a tree that is completely useless. So how do we solve this in Tezos? Well, in Tezos, we say a validator has to put up a security deposit for each block that they create. And let's say you put a security deposit for A, and this is at height 5. And now we've put some X amount of security deposit. If you sign a different block at height 5, again, let's say you change some of the transactions that are in the blocks, so the block hash changes at height 5 as well, then we slash your entire security deposit. So all of a sudden, there's now an economic incentive to not build on every possible block you see, but rather to choose the correct block according to the consensus. This is really important. Things like EOS and BitShares and Steemit don't have this. And due to that, like these systems are completely insecure in terms of how the underlying consensus and the civil protection mechanism works. Right, okay, now let me quickly take a picture that I can share with you guys later. Okay, picture done. Right. Right, quickly let's talk about governance and what has happened here historically in Tezos. So anyone can inject a proposal. Then we have 8 cycles for bakers to upload this proposal. In the future, we will also allow individual token holders to override their baker's vote, as long as you have more than one role as an individual holder that is delegated to a specific baker. This is actually something we're working on for the next upgrade. Then you have the next phase, which is the exploration phase. This again lasts 8 cycles. In here, so here you can have many proposals, and only one will continue to the next phase. Then during the exploration phase, you have to reach a minimum quorum, which is adaptive based on past participation. And then if quorum is reached and 80% supermajority wants to explore the current proposal, then we go into a testing phase. The testing phase is kind of funky because what actually happens, the product testing phase, the node will automatically spawn a test chain that anyone can use with the proposed protocol. So here we test things like, does it actually work in practice? Can people send transactions? And then any user can start testing on this testing, on the test chain that runs during the testing phase. And then lastly, what is it called? Proposal, exploration, testing. I'll call it approval phase. I think there's another name in the official docs for it. But the approval phase is effectively just saying, we've now tested this protocol upgrade. Do we want to upgrade mainnet to it? And if, again, here we reach quorum, which is adaptive based on past participation and 80% supermajority, then mainnet will upgrade to this injected protocol. And again, all nodes will automatically upgrade because they will download the latest, the source code from the network, compile it in a restricted subset of the OCaml compiler, and then dynamically link it into the running node. Quickly for the history of upgrades. So currently we are on, as of today, on protocol 006 or Carthage. Carthage was a housekeeping proposal that fixed sort of a bunch of things that weren't super nice, so small bug fixes. Before this, we had 005, which was Babylon. And Babylon was a massive protocol change where we effectively migrated the entire account state, because in the past, what you were only able to delegate from pay to ones, so from smart contracts, but they weren't actually smart contracts. There was just this weird structure where they didn't have any code and they were just used for delegation. And in Babylon, we migrated all of this. We also introduced ME+, and we also made Tezos ones delegatable. Before this, we had 004, which was Athens, which just tested out whether sort of the upgrade mechanism works, and it just changed the role size from 10,000 to 8,000. I still find it kind of annoying because before you could very easily see how many roles you have and go to how many tokens you have and vice versa, because it was power of it was in the order of tens. Now it's 8,000 per role, so the math becomes harder to do in your head. And before this, we had 003, 002, and 001, which were the original protocols. These were still effectively hard forks by which you upgrade, so we didn't have a governance process here. So Athens really activated the governance process, but these happened sort of in the first 3 months of the network. Yes. Also take a picture of this. Done. Okay, now the last part. So this is sort of a lot of background for how Tezos works, how the governance mechanism works, how the consensus works, how, yeah. And now we will talk a little bit about the actual thing, Tezos versus Ethereum. So one of the main reasons why, in my opinion, Tezos is a very decent choice for smart contract developers right now is because it's very unclear at this point in the industry on whether, on what the specific use cases are going to be that this industry actually solves for the real world. So really, this is super early. This is the internet in 1992. No one really knows what's going to be the next big thing. But with Tezos, you're betting on the fact that you have governance. So in Ethereum, we have a fairly static system that hasn't changed much since inception, but is currently trying to go from Ethereum 1 to Ethereum 2, which I like to compare to going from the Stone Age to straight to space travel. It's very unclear to me whether this will actually work. In Tezos, due to the fact that you have a governance process and an active core development community, you're much more betting on the fact that over time, Tezos will continue to evolve, and sort of as new and novel research and applications appear in this industry, Tezos is one of the only chains, actually I think currently the only chain, that has the ability to effectively integrate these changes over time. Right, so in Ethereum, so you have to bet that what is currently possible in Ethereum is what will be needed in 10 years. You have to do the same bet with Bitcoin. Bitcoin isn't going to change. With Ethereum instead, with Tezos instead, you can bet on the fact that it will upgrade over time in an incremental fashion. So instead of introducing incredibly large features, so you go from Stone Age to space travel, we sort of, every 6 months, we ship new upgrades that are useful for the network and that sort of iterate and improve upon use cases that we've seen in the real world. Due to this, as smart contract developers, sort of if you run into a problem on Ethereum right now where something is not possible because 3 years ago no one had designed for it, you're kind of stuck. In Tezos, if you have a real use case that currently the protocol can't support, it is very easy for people to bring this up and and the protocol and for us to adapt the protocol to that use case adaptation. Right? Imagine that adaptation. Yeah, it seems correct. Imagine right now you realize we need specific cryptography. Maybe you want to interoperate with something like Coda. Maybe you need the MNT6 and 4 curves. No protocol has access to them, like Ethereum isn't supporting them. It's not feasible to write that cryptography in a Solidity smart contract. If this is a real use case that a majority of the network has, it is very easy for us to add this into the next protocol upgrade. And then in 6 months from now, all of a sudden you have access to this novel cryptography. I think this is by far the strongest point for Tezos right now, that we are not clear yet what specific problems smart contracts will solve. And due to that, it's very hard to design a static system to solve all those use cases. But in the Tezos case, you can bet on the fact that the underlying protocol evolves over time in order to take into account these use cases. So some of the downsides that you have to be aware of deploying to Tezos over Ethereum is a lot of the tooling is a lot newer, so a lot less battle tested, right? So Solidity has been around for 30 years. It's fairly battle tested. To be fair, it's a shitty system, it's a shitty language, but it's a working language. LIGO, SmartPy, Lawrence, they're all much newer. Due to that, it's sort of, there may still be bugs. So just be aware, the tool chains haven't been tested by thousands of people yet. You are some of the first beta testers. On the other hand, this also gives you great input in how these systems actually evolve, how these tools evolve over time. Yeah, and the other thing is the standards in Tezos, for example, token standards are currently being formed. So again, sort of it's work in progress. But the nice part about this is that as an application developer in Ethereum, you have very little say in how the underlying system behaves. Right now in Tezos, you as an application developer can have a lot of input in how the system evolves and what the needs of application developers actually are. So just keep this in mind. Right, that is sort of benefits of Tezos versus Ethereum. That is a shitty slide, and I'm sorry for this. And then as the last thing, right, are there any questions? So this is effectively sort of a quick introduction to Tezos and applications and languages on Tezos. Are there any questions in the audience?
Questions? Nope. I guess we have we have a few minutes left, Adrian. So it might be time to conclude.
Yeah. So in that case, thank you very much. I hope you enjoyed this talk. I hope this format works. To say virtual conferences are kind of interesting, and I like them because they require less travel and less waste there. Thank you very much for listening to me. I'm Adrian, one of the founders of Cryptium Labs, and thank you very much.
Thank you, Adrian. Okay, so next any questions now? No? Okay, thank you. The next speaker will be, the next speakers will be Christian Rinderknecht and Rémi Le Sénéchal, I guess. Please come here. Use this. HDMI, it's here. Okay, that one. This one. Yep. Sure. Okay. Very good. So Christian and Rémi are working on the LIGO programming language in the LIGO team. So please, you have to speak very close to the microphone. Okay. Okay. And so let me try to keep this here for the. Okay. Okay. Good.
Display.
La caméra est là. D'accord. On va parler au public ici. Okay. Okay.
Tu les vois que là,
Ok, ça va.
So good morning, everyone, at least if you are in Europe. So my name is Christian Rinderknecht, and I would like to thank Michel Moni for inviting me here. Also, Adrian to have done the heavy lifting and talk about the protocol and introducing, in general terms, smart contracts. So can you hear me? Can you see my slides? Is it okay? All right, so I do have slides because I'm left-handed. No, I'm joking, I'm not. So this is not the first time I give this talk. I made some changes. I do, though, recognize some familiar faces, and it feels like I'm back teaching undergraduate students in college. It's kind of weird. So some of you are going to get bored, for sure. I think I used to have a longer personal introduction. I think nowadays I will just go by, I used to be Michel Moni's, one of Michel Moni's PhD students. And I passed, so I guess this is enough introduction. Thanks, Michel, for being so famous. Makes my talk so short now. So yes, so LIGO, tomato. Pick the one you like. It's at first it was the name of a project. It is one or many languages. I'm going to explain that for writing smart contracts on Tezos, other than writing Mikkelsen. So it's a high-level language. It's also a company that is now called Ligolang. You will see that there is a website as well. So what we have done basically is develop that language we call it LIGO, and also some tooling around it, because nowadays a naked language is of no use. So the other component you need to get a language adopted is tooling. Of course, you need also libraries and community, so we are working on that. But we started obviously with the language and the compiler and the tooling, because this was the minimum we had to do. To be taken seriously. So there is a website. You can see the URL down there, and so you're welcome to have a look when I'm speaking. Yes, we do of course training for people interested in writing their first dApps, or taking their first steps in writing dApps on Tezos. I'm sorry, I can't look at all of you in the audience because the location I'm with, so I'm not ignoring you on the right side. It's camera work, you have to keep your marks. Yes, so what do we mean by high-level language? We mean a language where you have variables, you have expressions, you can define your own data types, and you can actually destructure your data easily. This can be done, of course, in Mikkelsen, but it's more complicated. I mean, you can do anything on Mikkelsen, but it's very complicated because you have no variables, for example. So you have to keep in mind the order in which you put things in the stack and what it is you put in the stack, okay? So it's much nicer to have names to talk about things. So this is very much like a normal mainstream programming language, okay? Then, of course, this is currently this is not a general programming language. So this is a domain-specific language for writing smart contracts. And this may seem obvious, but this creates some tension sometimes. For example, we have in the audience and later on speakers from Madfish Solutions that are trying to target LIGO for compiling from Solidity. And this creates some tensions because some features you would expect in a mainstream language are not present there because it's still a DSL. So even though it looks like a general programming language, it doesn't have all the, the bells and whistles you would expect from a normal mainstream language. It is open source. And you're welcome to always to leave us some GitLab issues. Sometimes we are asked in the team to compare LIGO with other programming languages you heard about before, about SmartPy, Solidity, others, Juvix. Unfortunately, we don't know. We don't have time yet to look at them. I even found a dead Jira issue to compare us with SmartPy. So the situation is very dire. We haven't done the homework yet. We will do it when the time comes, I suppose. Well, we don't see others as competitors. Perhaps this is the good news of this. Why did I say earlier that LIGO is perhaps many languages? Because in fact, it looks like many languages. And from the inception, we didn't want bike shedding, useless discussions on syntax to to clutter the community, the future community of Lego. So we decided to offer different concrete syntaxes. So they do look like different languages, but they are not. Internally, the compiler is the same for the three syntaxes. And we went beyond just syntax. We wanted to offer different programming paradigm. So one of them is Pascal Lego, which basically offers you lots of keywords and the possibility to do a limited kind of mutation assignments, if you will. The second one is Cameligo, which is inspired by OCaml. So actually, it's a strict subset of OCaml. So it's pure. So you don't have mutation in that subset. So you have to know your purely functional programming here. And last is Reason Lego. The last added was Reason Lego. This is inspired by ReasonML, which is itself a syntax inspired by JavaScript, which is put on top of OCaml. It has quite a large community, perhaps as large as the OCaml community, so it's widely known. For those people, we have that as well. And to show you how rich this is, even within Pascal Lego, there are two flavors. Of course, this makes very important for us to offer pretty printing facilities. And even we plan to do a transpilation between syntaxes. So if you have a smart contract on Pascal Lego, say, you may want to have the same contract on Cameligo or vice versa. And this being done automatically for you. One of the reasons is because you always want your smart contracts to be as widely reviewed as possible. Remember, they are publicly available anyway on the chain, especially if you put them in a comment in the Michelson, which is possible in theory. And anyway, you would want them to be reviewed before you deploy them on chain. So for that, you don't want to perhaps be stuck in one syntax. If your programmer is not familiar with one, you can choose any other automatically. So I will be introducing very, very, very quickly, because we have very little time, the non-Tezos specific features. I picked some specific features that are non-Tezos specific. Rémi will talk about something, will explain some contract, right? So more practical later. Well, okay, so some interesting things. So when you call functions in Lego, arguments are copied, but also the environment. And inside the function, if you reassign variables that in an outer scope, the effect is lost when the function is finished. So it allows you some form of imperative programming, but limited, in a limited way. So from the outside, functions look as if they are pure. Of course, if you don't query the chain, all right? Because this is impure. This is specific to the way we program. We have higher order functions. I know this has become popular thanks to functional programming in the last 10 to 15 years. So we have lambdas, anonymous functions, and we can pass functions to functions and things like that. Even in Pascal Lego. Anyway, the original Pascal had already that from Algol. So there you go. Something we don't have is user-defined recursive data types, simply because we still don't have recursive functions. So we do have, what we did was to lift Michelson types, which are some of them recursive, like sets, at least lists you may aware of, and maps, lifted as predefined types in Lego. In the future, we plan to have very soon, I think, a limited form of recursion available for functions. So this is very general, but yeah. So let me show you. So we have variant types which are coming from the, again functional programming world. So here you define a coin as being head or tail, and what can you do? This is This definition these definitions are equivalent to enumerated types you find in many mainstream languages. You can go a bit beyond and associate some data to each case. So you can actually have data that is defined by case, which is very useful for many applications. So if you want to flip a coin, this is how you would write it in Pascal Ego. So you see you have lots of keywords. The feedback we have currently is that some people like it very much to have lots of keywords because they help them to keep in mind what they're doing. So I don't know, this is up to you. In Cameligo, so this looks exactly like in OCaml. This is correct OCaml and a correct ReasonML code, actually. And just the last feature I would like to show you before Remy goes and tells you more about one specific contract we have. So you get an idea of a specific application. Would be looping and how we do loops. So this is, I picked this very simple and I hope widely known algorithm to compute the greatest common divisor of two natural numbers. And this is how it looks like in Pascal Ego. So you see it's quite, I think, readable. You can see you have your while loop and you can reassign to variables multiple times, okay, after declaration. So we hope that this will be quite easy to grasp for someone who is used to an imperative language. Okay, so Cameligo is really like OCaml, so we don't have loops. By loop, I really mean a syntactic construct like this one, like while, okay, where you have a piece of code that is repeatedly executed until a condition is met, okay? Since we are in Cameligo dealing with a purely functional language, we don't have that because we don't have mutation. So if the condition is true, it will remain true forever. So loops would always either never be executed or always be executed, which is useless. So what do? We have a predefined functional iterator, of course. So this is the same program written in Cameligo. So you can see that we have a loop fold while, which is predefined, and it applies repeatedly the function iter until a condition is met. And how do we know the condition is met? Is because iter returns a pair. And the first component of that pair is actually a Boolean that tells you whether you have to stop or not. Perhaps it's clearer if we use a predefined function stop and resume like that. So this is what we recommend until now. Soon we will going to improve on this, but as you can see, this is pretty short and I think it's neat. All right, just to mention something about the backend of the compiler, we do have lots of optimizations. So the Michelson we produce is not ridiculous. Some cases we are doing changes to the way things are represented internally. So temporarily we may have some, too big a Michelson produced, but we work always on that. And for example, we have inlining. Okay, so you can suggest or tell the compiler to inline your function and some constants. The compiler is doing that, but you can also enforce it. So it looks it feels like a real programming language. It's not a toy language. Just a word on what we are going to do and we are planning to do. We are working on a new type system, much more powerful. Currently, we have you need to annotate a lot with types. Soon we will have much more type inference, so that will be more convenient for you, and you will have shorter programs as well. Adrian mentioned formal methods earlier. We already have been working on a certified backend in Coq, which means that at one point we will be able to extract in OCaml, because the compiler is written in OCaml. We will be able to extract the backend from a logical specification of what is a correct compilation. Okay, so this needs to be specified, and it's not completely clear now, by the way. But we have been working on this for a few months now, and so here we are. I think it's time for Remy to say a few words. I had this intended, but I think he will show you on the code itself. Thank you.
Sorry, 1 minute. Sorry, so I got to set up my computer, so just a moment. Yeah, that's great. So I cannot actually see what I cannot see the code actually. There is a screen in front of me and the font is really small. So I'm going to do a bit more settings. This is going to work. Right, can you see? Can you see everything? Yes. Yeah. Oh yes, yes, I will put a light team. Good idea. Okay. There you go. Okay. So, the idea here is to present a small contract, a crowdfunding contract, and to go through, if I have time, to go through an actual execution of it. Not on-chain, but with our dry run command. So, first thing you want to do when writing a contract, I believe, is to define some types. So, as you may know, a contract is taking a storage type that you can define, a parameter type that you can define, and the contract itself is a function that takes a parameter and a storage and returns a list of operation and the new storage. So the storage you get in the input is the initial storage stored on chain, and the one you compute is the new storage. So for our crowdfunding, we have a parameter which is a variant type, and so the constructors here are just well, the action we would like to perform. So there is just back, claim, and redraw. And what do we store in this contract? So we store the owner of the contract, which is an address. I mean, sorry, the storage is a record. And yeah, so in this record we have multiple fields, and one of them is the owner. The target is how much we would like to get in this crowdfunding project. The deadline is when the project is over. I mean, the gathering of the fund. The backers, sorry, are those who gave money, and this funded field is basically, I'm telling you if the project has been funded or not. Okay, so here I have, you see. Okay, so here you have some utility functions. I will go back to them later and show you actually the main function of the contract so that it's clearer for you. Okay, it's here. So this function is taking an action of type parameter, so it's either back, claim, or withdraw, a storage, which is the initial storage, and return, the type return, which is here, the list of operation, and a new storage. So what this main function does is it's matching on action, so the parameter, and dispatching to the few function I will show you above. So for back, for example, if you want to back the project, what we first do here is that we check that the deadline is not passed. If it's passed, then we throw an exception. I mean, you can see it as an exception. This basically tells you that the execution of the contract on chain will be aborted, and that nothing will be changed. So if the deadline is passed, we throw this exception, otherwise we skip. And then we are matching on the sender. I mean, we are trying to get the sender entry in the baker's map here that I defined. Sorry. So the bakers were a map of address to Tez. So we are trying to find the sender entry, and if the sender doesn't exist, then we create an entry for it. Otherwise, if you already donated, then it will just be skipped in this contract. Not sure if it's very good, but at least in this example, sorry, it's like that. So now, sorry, let me move this bar here. Okay, so claim. Same thing. We are going to do a few checks. So if the deadline is passed, or rather, yeah, if the deadline is not passed, then we fail. Yes, so here we check if the contract, I mean the crowdfunding, has already been terminated. If it has, then you cannot claim your money back. And here we check if you are a baker, because if you're not a backer, you cannot get your money back. So same thing. You have this if, then fail, which is kind of an exception, and then skip if the condition was not true. Here what do? We get the baker balance with this utility functions I will show you in a moment. So get baker balance is here. We need a lot of type annotation, as Christian has said, because the new type system is not here yet. So that's why you have to annotate here. You see an annotation. So this function is taking an address map, which is holding the binding between the address and the balance, and returns a balance. So you match, again, case. Find opt will return an optional value. So it's a variant type, an option. Basically some or none. So if it finds something, then it will return the binding of the address in this map. So in this case T. If it's not, it will fail. Couldn't get the backer balance. So again, we were here. So this is giving you the balance of the backer. This test, Tezos get contract, is basically checking here, in this case, that the sender, I mean the sender, sorry, has wait, what do we do here? No, it's just getting the contract, basically, to be able to create a transaction just after. So it's taking the sender, and it's going to, then we are going to create a transaction of this given balance back to the sender. Why do we assume that sender is a contract? I'm not sure I got the question, sorry. Okay. So I told you before that the contract is returning a list of operation, and this list of the operation is actually what will change the chain states. Where? Sorry. This one? Yeah, it's the because this function is actually expecting the contract, and this is checking the type of the parameter of the contract. So this actually type check the contract, saying the parameter of this contract sender is of type unit, or is an implicit contract, but I'm not sure you have. I mean, you went.
Yes, you can. You can transfer to contract with unit type. It's just transfer to user. If you transfer to simple address, you can cast it to contract type, but you just send message unit, which just, if you familiar with C, is just void.
All right, thanks. So yes, I was here. So yeah, you build this operation, which will be the transfer, and then you remove the sender from the list of the backers, and you return the operation and the new storage, which is basically the same, but with this backer removed from the list. And the third action you can perform is redraw. So when the deadline is reached and the target is reached, then you can, the owner of the crowdfunding contract can redraw the money. So what we do is that we check if the sender is the owner. In this case, we check if it's different. So if it's different, of course we fail, because only the owner can withdraw. Same thing here, deadline. It has to be after the deadline, and also the target must be reached. And then we are doing the same thing, so we are typecasting, again, the sender against the unit. And we are building the transaction back to the owner of the contract. And we are changing this funded field to true. And same thing, we are returning this operation and along with the new storage. Do I have time? 5 minutes, okay. So I'm going to show you a few execution. So I wrote a small script that has some commands. So Lego, as a command line interface, has multiple commands. So you have compile contract, dry run, interpret, and others. So you can check it out. So the first thing I would show you, if I can get my terminal, yeah, here. Okay, is the Michelson code that is generated if I compile this contract. So it's yeah. So I don't know if you have any experiences, Michelson, but this is how it is. This is a Michelson contract. So I'm not going to explain everything here, of course, but this is how it looks. Okay, and now I'm going to explain how to dry run a contract. This is here. So we call dry run on a given source file, of course. We give the source file here, and then the main function name. So here it was main, right? And we are giving a parameter. So we want to execute the contract here. So we are giving back, for example, and giving an initial storage. So I put some initial storage, let's say here, and I'm using it in the script. So it's called test back here and test back here. Okay. And then you can give some chain context, I would say, in order to do testing. So here you have the predecessor timestamp command, which is basically allowing you to set the time of the... Okay, I have to conclude, sorry, but no time for that. So, yeah, thank you. Yeah, You want to? Well, maybe I can execute the contract actually. I don't want to be the one that is late. So yeah, I will execute this, and you will see what happens. Sorry. Okay. Execute again. Okay. So here I first interpret the test back. So I have my initial storage. So this is a representation of what you wrote in Lego, but it's not actually Lego code because we don't have the syntax pre-printing yet. So yeah, you can see here that you have a map with multiple baker. The contract is not funded, and the owner is this guy, and the target is whatever. 100 million meters, something. And I ran this contract and I got fail with deadline pass because I called it with the timestamp that is after the one that is defined in the initial storage, which is here and which is not very well pre-printed, sorry. But yeah, so this was my first test, and this is how you can write some test in Lego. Yeah, thank you.
Okay, so thank you, Rémi, thank you, Christian. So we'll take a few questions. Yes.
I'd just like to know if you have a unit testing framework with Lego.
Okay, so this is a good question. So if you want to unit test a contract, the best way to do it, I would say, is to use another. I showed dry run, which is running a contract and checking that what you run is a contract and has everything that is needed. But there is another command line, which is run function, and you can run an arbitrary function. So I would recommend to, if you can, write your test function and execute it using run function. That's how I would do it. But you can also use dry run and parse the output of dry run. People are actually doing this, but yes, there is some work to do in order to have proper unit testing for contracts.
So follow-up question about testing. So with Lego, you have some virtual machine, yes, right, or some interpreter, which will execute the code with a storage, and you can interact with it without the blockchain, correct?
Again?
Based on what you saw, how do you run it?
Okay, sorry. So dry run, the contract is compiled to Michelson, and then dry run is calling the Michelson interpreter directly to get the results, and the results are...
So how do you do, like, if you want to have a sequence of some commands to run? And how do you test it?
Pass storage from previous to next.
So the storage is kept, right?
You just pass, you have storage state 1. You have an executed function. You have storage 2. Pass storage 2 to second call.
Okay, so I need to copy this storage, like the output of the of the run. Okay, so not very friendly.
There is Takita also.
Yeah, I wanted to say that. So if you want to test your contracts, you may use Takita. It is a JS library, and you may write your test normally and check state changes.
Maybe it's more general about Tezos in general, but I see that you output this wall storage at each time. But if you have like a lot of baker, I imagine that there is a kind of compression or optimization so that you don't store on-chain the whole map each time.
Oh, yes, there is another I mean, there is the map type and there is the big map type, which is actually stored as plain in the chain, but the access at least are deferred. I mean, the Michelson interpreter will just compute a diff with the old map and apply it.
Okay, but only the map is treated like that. The other storage types are just always written into the blockchain?
Yes, I believe. Yes.
Okay.
Thank you. I'm sorry we have to move on because we are late already a little bit. Let me add to the previous talk that they have a website, legolang.org, I guess. There is a Slack channel, so it's on the Slack, Tezos Dev Slack. Christian?
Yes.
Slack channel? Okay.
Yes, it's the same as Nomadic Labs.
Yeah, so you can get information from there, especially people listening to us remotely. Also, we'll have a break in 15 minutes, and that will be a great opportunity for the developers to discuss with the Lego people. So thanks again, everyone. The last slot of this morning, I don't know, can you display my screen, please? So before the break, we have a 15 minutes kind of lightning talks by 5 companies that are using or are interested in using Tezos. So the initial order of presentation, we plan to start with Equisafe and then NeoFacto and then Octo and then Skilled and then Sword. Equisafe will be a little bit, so we'll rotate the thing, and we'll start with NeoFacto TK next. Laurent Kratz, I guess, will give the presentation. So Laurent, let me prepare the screen. Just have to hit space. Okay. You have 3 minutes.
Okay, thank you, Michel, for having us. So my name is Laurent Kratz. I'm the CEO of NeoFacto. NeoFacto is based in Luxembourg, headquartered in Luxembourg, but we have also offices in Brussels and Paris. We have 20 years, and we are in the blockchain space since 2013. We've made lots of things. Our customers are mainly banks. One of the main reference we have, thanks to Romain and his team, is Société Générale Forge. But we also do things with Clearstream, with others. Anyway, so it's not related to Tezos. So the point is to speak about what we do with respect to Tezos. So the main project we have already, and the team is there. We have Khaled, Safwan, Mohamed, and Fred is not there. Fred is in Brussels today. So we have a project inside the company called TK Next, which is about doing a complete platform that helps to do decentralized finance. In order to do decentralized finance, you need both. On one end, a stable coin. On the other end, structural instrument like swaps and bonds and so forth, and do everything called DVP, delivery versus payment. So the first step is to have a stable coin. So the project we do now with Nomadic Labs is to build, the name is Eurotez. I don't know if we will use that logo, but it's one of our proposition to build so on top of Tezos and using the embryon of smart contract called FA 1.2 fungible tokens, but we had to extend it because in order to do something equivalent to RC20, we needed, for instance, events. And so it's some kind of extension of FA 1.2. The point of this stablecoin we developed together with Nomadic Labs is that it's a stable coin where the collateral is able to be checked real time thanks to open banking. For the ones that are a bit aware of that, it's a European Commission directive called PSD2, Payment Service Directive 2, whereas any bank have to provide an API for free to double check to access your account. So the point is that we have a gateway that check real time if the number of tokenized euros is equals to the number of euros that are in escrow at BNP Paribas because we use the sandbox of BNP Paribas. So this is the point, and for now, the other interesting technical point we have in the project that the smart contract we provide are feeless. They are not feeless per se with respect to the blockchain, but in terms of user experience, the ones that are using tokenized euro do not need to have any Tez. Okay, it's up to the gateway to pay the fees, right? So it's based, so the contracts are developed using SmartPy. It's currently on the testnet. And we use both Taquito for the front end to the blockchain, and also with respect to the middle tier that does a little bit of software with OpenPSD, Open Banking. It's written in Java. Okay, so the next step would be probably go further and do the DVP part. Just a quick topic on ScoreChain. So ScoreChain is one of our spin-offs. The company we started in 2015. We are #1 in Europe with more than 100 customers. It's about doing compliance and anti-money laundering. So for sure we do a lot of stuff around Bitcoin, Ether, and other cryptocurrency. But now we are working also to build the Tez part of ScoreChain. Voilà. Thank you.
Thank you so much. It's a difficult exercise to be so short, and I'm sorry about that. The next presentation is by Octo Technology. There are two people. I'll let them introduce themselves.
Hello, I'm Emeric Betancourt, and this is Lutheron. We are from Octo Technology, a company that's doing consulting and delivery, and we are more than 600 consultants in tech. We've done a lot of projects in blockchain, including private blockchain. We work on Corda, Fabric, and on the public blockchain. We've done a lot of projects on Ethereum and Tezos. So today we're going to present you two projects that we are doing for Tezos. The first one is Tezos Academy. .io, and it's a fun interactive tutorial to learn to code Lego. I remember that I really liked to learn Solidity with Crypto Zombies, so we saw that Tezos needed the same kind of learning platform. So I invite you to go to tezosacademy.io. I won't have time to show you right now, but you can see that we have a non-fungible generator on the first chapter to generate a little spaceship. And then in the next chapter, you're going to write the smart contract to have the ships go into battle. So the goal is really to attract developers and embark them in learning Lego and deploy the smart contract for Tezos. And I'm going to give the speech to Lou for the next other platform.
Yes, and our second project is called TezosLink.io. So we will release it next week, I think. So it's Tezos API, so basically a Tezos gateway to offer a better developer experience. So we handle scale out of nodes, caching, and so and also a dashboard to show some metrics about transaction usage. So the front-end, back-end, and infrastructure code is open source. Anyone can deploy it. We don't want to be a centralized gateway to the Tezos network. So that's all.
And just to add, all the platforms are free and open source, so you can go check the code and maybe do some pull requests or give us some feedback. We are really open to it and want to implement them by the end of April.
Thank you very much. You left some time. Great. So the next presentation is about skills. Laszlo will present his profile.
Hi guys, can you hear me? Cool. So it's a bit small, maybe. Oops, sorry. Okay, I don't touch anything. My name is Laszlo Sebo, like Nick Sebo, for those who knows, right? But he's not my uncle, since I have more Tez than Bitcoin. And I'm actually the CEO and co-founder of Skills. At Skills, we deploy and orchestrate blockchain at your fingertips. We work with Ethereum and Corda as well. What we realized is that when a company or developer want to use the Tezos network for its use case, there's 3 stages. The first stage is, do I need the Tezos chain for my use case? The second stage is the deployment part. And the last part is the application part, where you will obviously use a smart contract, Smart Pi, Lego, or Michelson. And on the deployment part, it's obviously for a company a very long process to deploy the network, since you have to centralize your full node. If you centralize many full nodes, it can take like a few days or even a few weeks. It's also a very expensive process, since you have, if you want to put your critical application on it, you need to get high availability. And high availability, you know, in any blockchains is kind of tricky. And last but not least, external providers are usually APIs, and we think APIs is a super centralized way to connect to the blockchain, since, you know, you have to bet on a startup that this startup will not die, and if the startup dies, your connection to the blockchain dies as well. So what we do is, like, we deploy blockchains very easily. We try to spin up full nodes in a few minutes. We deploy, you know, many full nodes in order to orchestrate them and to have like a 3-9 availability. And we save 75% of cost of deployment and maintenance. Maintenance is the big part. And last but not least, we deploy in your stack, so meaning public cloud or private cloud or on-premises, so we're not the single point of failure between you and your blockchain connection. So yeah, the kind of use case you can put on our infrastructure are obviously, you know, asset tokenization, sorry, or data inscription on chain. We think as well we might improve the private Tezos part for use case like KYC sharing between banks or insurance company in the future. And we are a team of 7 people in Paris, and we're happy to discuss about what we do afterwards during a coffee. Thank you very much.
Thanks a lot. The next lightning presentation is about the Sword Group company. Alain will.
Hello. So I guess you won't be able to read anything. My name is Alain Broustaille. You can find me on LinkedIn. This is Sword Group. Sword Group is an international IT services and software vendor. We present in 19 countries with more than 2,000 people, including 600 in France. We are historically experts in electronic document management. We've got 1,000 of clients with lots of different kind of projects, including digital signature. Digital signature is a very fast-growing market. You can do it in different ways. And one way we particularly like is writing and putting a proof of documents in a blockchain. So you may have heard about document notarization, document anchoring. We've done that in the past with Bitcoin, with Ethereum. We like it. It's easy. You use the feature of the blockchain, which is a strong authentication method, which is an immutable way of storing the proof, not the document, but the document hash, technically talking, or hash of hashes. And the fact that you have timestamping on it. If you do it correctly, it's in line with the European regulation. Doing it correctly is not that easy, because it's not the same case if you sign 1 document or 1 million documents. If you sign yourself or you sign on behalf of your client, if you sign it for an individual or for an organization. So we've been through that, we presented it, we've done some successful projects with clients, and they told us, especially the big groups, institution, public institution, we need a blockchain that is ecologically responsible. We need a blockchain with a clear governance, and we want to be able to audit not only the smart contract with the blockchain. So the Tezos choice is a clear choice for us. We are going to implement a solution to all our systems to sign digitally documents in Tezos. But we don't want to do it alone. It makes no choice, or let's say it's much better if we can use the same standard all together. And the timing is perfect, because today on Tezos there is not many projects on document notarization. So what we want with you, community, startup, if you have project on document notarization, we'd like you to come to our project. It's an open source project. We want to build a smart contract, open to all, so everybody can use the same smart contract to sign 1 or several documents. Everybody can use it to check the documents. So I'm signing, you can check my signature. We want to build some open source connectors to interact with the blockchain from outside the blockchain, because your clients and my clients don't know anything today about blockchain. We want to build a format, a data model that will fill all the different use cases, and signing one diploma is not the same as signing 1 million invoices. So please come to us, come to me, to the team, come to the foundation or Nomadic Labs, but we'd like to know your requirements so we can propose something that fits both our needs and your needs.
So we had another. I'm sorry, it's so small. Okay, let me fix this or try to fix that.
Thank you.
Yeah.
Thanks a lot. Okay, so good morning, everyone. So we at EquiSafe aims to bridge the gap of knowledge that have investors on non-listed companies on their positions on these non-listed companies on the one hand, and on the other hand to provide tools for companies to ease their corporate management and their investment processes so that they can onboard easily all the investors on the company on the one side, and on the other side to have a complete view on their cap table management and provide them tools for to ease all the process of General Assembly, voting procedures, dividends, and coupons for debt. So that's our vision at EquiSafe. So we rely on blockchain to provide a share ledger that is legally binding. That's one of the main advancements in the legal area with blockchain. It's the loi Sapin 2 that gives us the ability to enshrine all the share ledgers directly on blockchain, and you don't need anymore a paper-based version of your share ledger. Share ledgers are those papers that give you the list of the shareholders and any kind of other investors in the company. So we have started working with Tezos on September 2019, and we released on open source our standard, the NIC standard, so that provides you tools to be able to issue your own securities directly on Tezos. The main event that happened no later than last Tuesday is the tokenization of an annex of the Château de Versailles, the Trianon Royal, and we are very proud to tell it for the first time here in Paris. That happened in New York at the consular, the French consular, and you will hear a lot about it in the coming days. Thank you very much.
Okay, so thank you to all speakers at that particular session. It's a difficult exercise to be so short about such exciting projects, so let's thank them again. If you want to enter in contact with them, they will be here at least during the break. The people who are listening to us, watching us remotely, you can contact us, the organizers, or maybe grab their websites or contact information on their slides if you want to enter in contact with them. Thank you very much. We have a short break, 20 minutes breaks, and we start at 11:10 with a talk about Smart Pi by Roland. Thank you.
ce serait bien de parler dedans parce que souvent, en fait, vous pensez à autre chose et vous êtes, par exemple, vous parlez comme ça. Et le micro est à côté.
Ok, moi je vais faire cet effort, mais je peux. D'accord.
Bon. Alors.
Tu avais utilisé tous les smartphones que je t'avais donnés?
Oui, il y a 3 smartphones utilisés.
Ok, donc un dernier.
Toi, tu utilises le tien, j'utilise.
Donc un dernier, il faut que je trouve effectivement.
Allez, mets ta version. Faut juste me passer après le.
C'est vrai qu'en théorie, maintenant, avec le NDI sur le smartphone, je pourrais lui donner le PGM. Je pourrais lui donner exactement ce qu'il y avait en tête.
Ah ouais.
C'est encore mieux que rouge.
Ah oui. Pour un cadre, c'est pas.
Non, c'est pas conseillé.
Ça va trembler, ça.
C'est possible de mettre la discussion en troisième micro?
Dans le circuit en troisième micro.
Là tout de suite maintenant? Ouais. En fait, on s'est rendu compte que l'animateur, ce serait bien qu'il ait son propre micro. Et
après, on disait peut-être qu'il peut faire. Il utilise un des deux micros pour lui. Et après, il y a celui-là qui ne bouge pas. Pour tous les autres intervenants. Et bon, il y avait un autre direct parce que ça passe bien.
Ça reprend à 11h10, c'est ça? Il y a un peu de temps, hein. Il y a 15 minutes.
C'est pas un bras magique avec l'accroche téléphone.
Bah oui, je sais pas ça. Tu veux l'accroche aussi, l'accroche chou là? Ouais, non, pas ouais, non, pas la peine.
Après, du coup, il faut juste que l'adresse.
C'est ça, ouais. L'adresse IP. Donc l'adresse IP.
Ouais, c'est pas mal, ouais. Ouais. Ça manquait d'une heure pour s'installer, genre en toute sérénité, mais sur la dernière.
Ça manquait aussi d'un mois pour vous préparer.
C'est possible. C'est vrai que tout ça s'est fait vite. Hein.
Mais ouais, non, mais c'est.
Tiens, c'est 10.1. Bah, déjà, il faut que tu te connectes sur le Wi-Fi là.
10.1.
Tu t'es connecté déjà au Wi-Fi?
Je me connecte.
Bon, comme ça, c'est très bien. Elle a son truc.
Ok, c'est bon. 10.1. Non, 10.111. Ok. Point 104. Point 104. Point 12. Point 12. 2.8088. 2.88. 8088. 8088. Ok. Slash Toli. T-A-2-L-Y. T-A-2-L-Y. Et tu mets CAN2 FS5 TeleRubj. Tali à la fin?
T-A-2-L-Y.
Ok.
Slash Tali.
10.111.104.12. 2.8088. Attends, regarde.
10.111.104.12. 2.81. T'es bien connecté à Internet? Là, ouais. 104 ou 114 t'as mis? 104. Ah. Non.
J'ai pas l'impression. Il n'y a pas un petit truc avant le. Je te laisse gérer. Ça va marcher.
10.111.104.12.
téléphone, si c'était connecté parfaitement, quoi.
Ouais, mais attends, mais je vais tester. Ouais, il y a une connexion internet, ça n'a aucun sens. Sinon, je vais essayer, mais pas avec Google, je vais essayer avec un autre truc. Copier.
Bah. Voilà.
Ouais, chelou ça. T'es sûr que t'en vois?
Alors, on va repartir. Coffee break. Je sais, Roland, pardon. Roland, tu m'entends? Pas sûr.
Je crois que votre micro est coupé sur
Ah, moi je suis muté, oui, pardon.
Ouais, ouais.
Roland, tu m'entends?
Ah, c'est bizarre, ça se connecte pas. Même moi.
Alors peut-être que mon micro est vraiment coupé. Microphone, internal microphone. Roland, tu m'entends? Bon.
Je pense que c'est de notre côté, il faut qu'on change le HDMI. Combien de temps on a besoin pour savoir l'interview? Je sais pas.
Là, on va partir dans une minute, 2 minutes, on va chercher des gens et...
Ah bon? Ok. On n'aura pas une image du coup des gens qui parlent.
Ah, il y a du son d'écho.
C'est mon micro qui... Donc là, on est tous... Non. J'aimerais bien être sûr que Roland... The sound that just dropped.
C'est normal. C'est notre micro, je l'ai muté, parce que c'est un qu'on nous entende en fait. Parce que regarde, il nous entend. Enfin,
Non, mais là maintenant, il a envie.
Ah, c'est toi qui donne le son de lui? Faut parler.
Ouais. Ok. Alors, on est... moi, je reste muté. Roland, est-ce que tu m'entends?
Oui.
Super. Bonjour. Alors écoute, je prépare la machine, je la tourne pour que tu puisses... Et je vais chercher les gens dans la salle, donc tu as encore 2-3 minutes. Super, merci d'être là.
Tu m'entends bien ou je change de microphone
Là, ça me paraît très bien. En fait, je t'entends pas dans des oreillettes, je t'entends dans la sonorisation de la salle. Donc là, tu parles à toute la salle où il y a personne, mais t'en fais pas. Tout va bien. Tout va bien. Ok. Alors, donc ça, ce sera la salle.
Très bien.
On est plutôt une cinquantaine en fait, puisque Emena a fait recommander les sandwichs. Donc, ok, c'est bon. Écoute, je vais chercher les gens et puis je te présente aussitôt.
Très bien, à tout de suite.
Ouais, bah, sur YouTube, c'est toujours en train de tourner, mais c'est le carton d'attente. D'accord, d'accord. À un moment, on va tout réouvrir.
Ok. Donc là,
Il y a un bruit de fond, hein, mais...
Ce micro-là, est-ce qu'il, quand il n'y a pas de questions, on le ferme ou Alors, ce serait celui-là normalement. Ça devrait être celui-là.
On est toujours sur la base de 2 micros. Mais c'est vrai qu'en fait, il y en a un qui n'a pas été téléchargé.
Ouais, parce que si on a contacté le mec, il faut qu'il ramène un micro là. Mais il n'y aura pas de souci pour le connecter aux autres ou...
C'est lui qui nous le donne.
C'est lui qui le donne.
Ok. Benjamin, on est bon? On commence, là, les gens vont arriver, hein, tant pis. Ok. 5 secondes. Non, mais là, enfin oui, je vais...
Ce serait mieux.
C'est mieux que là? Si je fais des efforts. J'attends l'image là. Okay. I don't see the image, but yep. Okay. So we are back to our Tezos Developers Day. This is the second session in the morning. We start with a remote presentation by Roland Zumkeller, who is currently in Italy, I guess. Roland will introduce us to the SmartPy programming environment for Tezos smart contracts. Roland?
Hello. So as Michel said, this is a talk about SmartPy, and I have very few slides, so I hope you can see them. And so SmartPy is a library that allows you to write smart contracts for the Tezos blockchain. And as Michel already alluded to in his brief introduction, it is also an environment that allows you to do other things. So you can test your contracts locally before you deploy them. Then you can actually deploy them after compiling them to Michelson. And once your contracts are on the chain, you can interact with them. So I'm going to show you this in a minute, each one of those. And just one more slide before about the architecture of SmartPy. So SmartPy consists of a core that is written in OCaml, which we call SmartML. It is currently not exposed to the user, so you don't really need to worry about it, but it may be in the future. SmartPy, as the name implies, is Python-based. So just like NumPy, you can import it as a library, and if you already have some development or a website and would like the ability to deal with smart contracts, you can add it. And but given this architecture that we have a core written in OCaml that takes care of all the symbolic manipulation, we plan in the future perhaps to also have other front ends like JavaScript would probably make sense. And finally, there are two different ways to do SmartPy. So you can go to the website, smartpy.io, and there's an IDE on there. And there's a command line interface as well if you prefer to live in Emacs and the Unix world. So let me change the visible window. 1 second. can you see my web browser?
Yes, it's fine.
Okay, great, thanks. So this is what you see when you go to smartpi.io. Well, let's write a smart contract. So I'd like to start with something very simple. So we first import SmartPy as a library. Then we define a class. So the first contract is just going to be a trivial contract that counts how many times it has been called. And so we inherit from the contract class. This is what any SmartPy contract inherits from. Then we define a constructor. Okay, so it's just a regular Python constructor.
Roland, maybe you can enlarge the size of the font, please?
Yes, thank you.
Thank you.
How's this?
Yep. That's fine.
Okay, great. So here we're calling self.init. So this is calling the constructor of the superclass with one argument, n, initialized to 0. So that means we allocate storage for one field that we call n. And this is the storage that is going to be stored on the chain. Now, what else do we need? We want an entry point, of course. So for writing an entry point, you call this decorator first, and then you write a method. So we are going to have one method that we call increment, okay? And all it's going to do is to increment this counter n that we defined above by 1. Okay, so you have to write self.data .n. I'll get into why a little in a bit. So that's our smart contract for now. We initialize the counter to 0, and every time we call the entry point increment, we increment it by 1. Now, in order to do anything with it in SmartPy, you have to define a test first. So here we go. We going to do just that. So a test pretty much always starts by creating a scenario. So a scenario is a thing in which you can do all sorts of experiments locally. You can create contracts, call contracts, have contracts call each other, etc., and simulate it locally first. So I'm creating an instance of the counter contract that we defined above, and I'm going to add it to the scenario. So this is done like this. And furthermore, I'm going to call the increment entry point once. All right. Now I click here on run. And let's see, is this readable? Yes, so we're getting back a lot of information. So first, initially the balance of the contract is 0. Let's not worry about that for the moment. Then we see the initial storage, which, no surprise, is 0. And then here SmartPy parrots back the just what we wrote. This is sometimes useful if for more complicated contracts because of the nature of SmartPy that you do meta programming. It's sometimes good to know what SmartPy actually understood. But I'll show you an example of that in a bit. Then we have one interaction here with the contract, which is the entry point increment that has been called once. Now we can add a, and importantly, the storage afterwards is 1, as you might expect. Let's do this again. So let me add 2 calls to increment here and run this again. So this has now been updated here, and we can see that there are indeed 3 transactions, and each time the counter increases by 1. Okay. I should also mention that we have a reference manual. So here you go. You can find it in the help menu. There is a dark theme. If you prefer to work at night, that might be handy. And there is a set of examples, which I guess I have to zoom out just to show you this menu. So you can load templates. If you click one of those, a smart contracts load, and you can explore what it does. Now, this is still a bit boring, having just an incrementer by one. So first of all, let's make some changes here to make this slightly more interesting. So I'm going to add a parameter to the increment entry point, okay, which we call x. And instead of 1, we're going to increment by x. I could run again. Now I'm getting an error because here I forgot to specify what x is. So let's increment by 1, and by 5, and then by 2. Okay, so, oh, I'm sorry. This is actually you don't write the if you have a single argument, you don't write the name of the argument. Okay, so what else can we do? We can look at the output here. So there's the Michelson code, of course. So this is the result of the compilation. And so you can see the Michelson instructions, and on the right, each time for each instruction, you get the you get the current stack. So initially, you have the parameter and the storage. After a dupe instruction, you get just the same thing twice. And then you project on the right, you have only the storage on the top of the stack, etc., etc. Okay, and then we have a types tab, which tells us a little bit about what the contract looks like from the outside. So it tells us that n is an int or a nat. So we have type inference going on here. You don't actually have to write types, but SmartPy infers them for you. And then there's a single entry point that takes an integer or a natural number. Okay, let's add another entry point. And this time, well, let's decrement instead of incrementing. And let's look at the code again. So here's what the compiled Michelson for this contract looks like. So this if left here distinguishes the two entry points. You have a comment here that explains which one is which. And then, well, you can see that for the decrement entry point, you call the sub instruction, as you would expect, and for the increment entry point, you call the add instruction, as you would expect. Now, Christian, I think, mentioned this morning that there was not much time to compare things between Lego and SmartPy. I thought we might just do a little bit of that. So here is the same contract in Lego. And here's the compilation result on the right. Some things are similar. You have the if left instruction and well, subtract and add. If you carefully count the instructions, you will find that there are fewer ones here. So we have 1, 2, 3, 4, 5, 6, 7, and well, 1, 2, 3, a little bit more here. So of course, this is constantly evolving, and I know that at Lego, people are also working on improving the compiler, but and this may look very different in a month. I just wanted to show it in the spirit of friendly competition. All right, so enough counting. Are there any questions up until here? Okay.
No.
So Oh yeah, I wanted to show you something else. So in scenarios, you can also not just call entry points, but you can also verify conditions. So for example, if after calling increment once with 1 and then again with 2, you want to check that in fact your storage now has a certain value, maybe probably 3. So let's just check that. Okay, going to write that here and run again. So nothing happens here because the condition is true, but let's say I have a bug in my increment function, and instead of incrementing, I actually decrement. Then this is slightly odd. Oh, I'm sorry, I called it is s.verify. Okay, so now I get, as I expected, an error. So it's telling me this condition is violated, and it's line 22. I click here, and it takes me to that line. And also on the right-hand side, you can see the error message. So this is useful for testing. You can also do really create arbitrary HTML on the right-hand side. So if you, I don't know, to add a headline here, you can do that. And oh, I still have the error here, so let me fix the increment function first. So here now I have this coding experiment from here, the headline. Okay, so that's all of it for the counting. Oh no, one more thing. Of course, we want to deploy the contract, don't we? So let's do that. We go back to the Michelson tab here and click on deploy contract. Okay. Here you can enter your private key. So here is a bunch of private keys I have prepared. Let's take one of them and paste it here. And now here's some settings. We don't need to change any of them for this contract. So I'll just click on deploy contract now. And I can see the result here. So it's already applied, and it gives me the address of the contract. Now let's explore the contract. So I click here on Open in Explorer. Here you can really type in any smart contract address, be it a smart Pi contract or legal contract or whatever. And it will give you some information about the contract. So this is similar to other blockchain explorers like Better Call Dev, video, whatnot. But I can also interact here with the contract. So if I want to increment, I tell it, well, increment by 3, build the message, and sorry, I entered my key again here. And I'm sending the transaction to the chain now. Okay, so it tells me status applied, which means the transaction went through. So as we can see here, the initial storage was 0. If I now reload that page, it is still 0, probably because it's still making its way into the chain. But if we reload in 20 seconds, I promise it will show 3 here. Oh, there we go. Okay, and we can view the operations also. So this tells us there was a single operation at this time and date, and successful. We incremented by 3, and afterwards the storage is 3. I should mention, if you want to try this at home, you need to obtain a private key first. So to do that, you just click on the Tezos faucet importer here. and you follow the instructions. So you go to another website, you need to copy and paste something, and you will end up having a private key. Okay, so let me close these, and let's do something a little bit more interesting. What every one of these seems to be doing these days are fungible assets. So here's a simplified fungible asset contract. So let me briefly go over what this does. This contract has two fields. We specify an administrator, and that has some sort of special powers, and then we have a ledger of balances. Okay. So let's look at the types right away. So I click run. SmartPy should tell me what the types are. So it tells me that admin is an address. So everything starting with a capital T is a type. And so this is a type of just the Michelson types. So we have an address and a ledger of balances, which is a big map that for each address that has deposited coins with us, we have that number of coins on the right hand side. Of course, these are not Tezos coins, but the coins that our asset represents. Then we have two helper functions. Okay, so increase balance, which, for an address X, increases the balance by a certain amount. So the way this works, it first looks into the balances data structure, whether X already has an account with us. If so, it is increased by the amount. If not, we add a new entry into the ledger, initialized to the amount. Similarly, to decrease the balance, we first compute the balance, the new balance. Then we check that it is positive. So sp.verify is a command that checks that a condition is verified, and if the condition is violated, it fails. So then the whole transaction will abort. Then we check if all the money that has been withdrawn, the entry in the ledger is deleted, and otherwise we update to the new value. So note that these two methods here have not been annotated as entry points. So these are just helper functions. Here are our entry points. Transfer allows someone to send a certain amount of coins to a destination. So destination is an address. So you can see that here also you have the types of the parameters. So amount and dest. Amount is an integer and dest is an address. So it decreases our balance. sp.sender is the caller's address, and it increases the balance of the destination. By the way, the order of these doesn't matter. So there's this classical problem, if you will, of something failing between these two that you find in any computer science textbook. Does not apply here because in Tezos, transactions are atomic. So if something goes wrong, the whole thing will go wrong. And the second entry point we have is mint. So this allows the administrator to mint money. So importantly, we have this line here, and which verifies that the sender is the administrator. So that means if somebody else tries to call this, it should fail. Only the administrator can create money. Okay, so that's the contract. We have an administrator, a ledger, and it means to transfer tokens, and means to mint tokens. Now let's test this. So here's the test case that we defined. We have 3 addresses, and we do the usual setup here of the scenario. And then the interesting part are these 5 calls here. So we first call, have the administrator call the mint function. So if you remember, I don't know if we still have the previous example. Yeah, here we just call an entry point c.increment. That's it. Here we call the entry point c.mint and also say .run sender equals admin. That means we're wearing the hat of the administrator for this call because it's important who you are. So this is determining the value of this SPSN here. So what happens here? The administrator mints 5 coins for Alice, right? Then they mint 5 coins for Bob. Then Bob, notice that this is Bob here, sends 3 coins to Alice. And then he does just this again. And finally, Bob is trying to mint money, namely 100 coins. So let's see how this plays out. So we have the transactions here. And let's see. So this is the first call. So you can observe that this address here with the MK at the end is just the administrator's address. So this corresponds to the first call, the minting 5 coins. The balances in the ledger are updated. So now we have the key and the value here that represents just 1 entry. Then the administrator does the same thing again, this time for Bob. And now we have 2 entries. So each of Alice and Bob have coins. And third transaction, Bob sends 3 coins to Alice. Well, as you would expect, the values are updated. So Bob now has fewer coins, Alice has more. And then, so you can already see this is in red, and instead of OK, it says KO. And we have a violation of a condition here. Why? Well, because Bob ran out of money. He has only 2 coins and is trying to send more to Alice. And so therefore, this condition gets violated. So if you click on line 16 here, it takes you right there and you can see what went wrong. And then Bob becomes completely desperate, is trying to mint money. And well, of course, it doesn't work because the mint function checks that the sender is the administrator, which Bob isn't. So this valid false, I should mention here. So without this, let me just delete this and run again. So I get an error. So in order to say we expect a failure in this test, so we want to test that. So failure can be desired. So clearly you want the contract to fail if somebody else tries to mint money. So you can test such things. So I promised you that there's not only a website, but also a command line interface. So let's have a quick look at that. I just need to switch my screen again. Can you see that? Yes, you can. So here we have exactly the same file, just the same thing that I just showed you in the browser.
Roland, if you hear me, can you use bigger fonts and maybe use reverse video or something like that? Black on white is better than gray on gray.
Oh, okay. Sure. No, sorry. Oh, yeah, of course. I just need to go here.
Well,
appearance would it be, wouldn't it?
At least make it bigger.
All right. Oh, here we go. Colors. I will also make it bigger. So let's change the background to white. I'm clearly not very good at this. No. Oh, there we go. Oh, I did it for the wrong one, so. Okay, this is slightly better, yes. Okay, there we go. And let's make it bigger.
Perfect.
Okay, sorry. So as I said, we have this one file here, and now we're going to call SmartPy on it. So SmartPy at the moment has a wrapper script. So when you just call this with help, it will give you, well, a help message. And what we're going to do now is just test the contract. So we're going to specify this contract file, a Python file, and then output directory. So let's do that. We had this fungible asset file, and I'm going to use the out contract directory. Okay. So now we have created a directory which contains a bunch of files. So let's look at two of these. First of all, just the contract code. Okay. So this is exactly the same thing that we just saw in the browser also. So this is just Michelson compilation result. And then also the test.output file that we have the exact same 5 transactions. So the administrator minting coins, then Bob sending them, etc., and also the expected failure here. And so it's functionality-wise one-to-one with what you can do in the browser, except for that this is more convenient if you want to automate tests, so you don't need to click your way through all the buttons every time. All right, so let's look at yet another contract. This time, the idea is to show you what we mean by metaprogramming. So, metaprogramming really means that you have a program that writes a program, if you will, or in this case, a program that writes a contract. So, let me first introduce briefly this contract here. So, this is a game of tic-tac-toe. Okay. So we have a board, a 3x3 board, which initially has -1s everywhere. Then we have 2 players, 0 and 1, and then we have the field next player, which remembers whose turn it is. Okay. There's a single entry point here, play, which gives you what you need to play, and you have to specify a row and a column. So there are 4 parts here. So the first part is we simply check that the game is not over and that only the player whose turn it is can play. Okay.
Roland, we see only your terminal window here.
Oh, that's terrible. Okay. Sorry, I forgot to switch it. Thank you.
Thank you.
Okay, thanks. Okay, so yes, tic-tac-toe, 3x3 board, 2 players. Here we remember the next player. Let's have a quick look at the types. So the board, so a matrix, 3x3 matrix is represented in SmartPy and I guess Michelson as a map from integers to a map from integers to integers in this case. Okay. Then the next player is just an integer, which will be 0 or 1 all the time. And then this 2 element list is also a method, really. There are different ways to do it. So you could have used a list here also. You could have 2 separate fields for player 1 and player 2. These have different implications for just how simple the implementation is. All right, so when we play, we first check that the game is not over and that it's indeed the player's turn. So the sender has to be the player that whose turn it is, I guess. And then we have, well, we make sure that the cell hasn't been already taken, that we check whether the game has been won. So here we check all 3 columns and all 3 rows, and then we check the 2 diagonals. If somebody has won, well, then we send them 1 unit of Tez and set next player to -1, so the game is over. Otherwise, we switch from player 0 to player 1 and vice versa. And here's a helper function check rule, so you can define helper functions in Python and call them within your contract. All right. As I showed you before, you can run the scenario. So I defined a scenario here with where Alice and Bob just play a turn, and you end up with a board. So here, clearly Alice is going to win. And here's the board. So it's also shown in a nice 2-dimensional fashion. We don't have too much time left, so I'm going to go on to the next bit. Oh, sorry, I promised you meta-programming, so let's do this quickly. So there's a notion of misère, so misery. So any game, you can define a variant to it, in which the goal is to lose. So when you play the game, you're trying to actually lose. So with chess, this is very interesting. Tic-tac-toe, a little bit less, but let's do it anyway. So I'm going to, so what I could do now is simply add a Boolean field here to the storage, right? That tells me if I want to play tic-tac-toe as a misère game. If it is true, then we invert the winner. So let me write actually that part first. Okay, so this is the bit where we determine the winner. So I'm going to write here, if we are in misère mode, then the winner is not the one who made the last move, but, well, the other person, the other player. And if not, then let's do what we did before. Now, when we create the contract, we want to specify whether this is, we are in misère mode or not. So I could add this now. Let me actually just briefly write this like this. Okay, so this would add a fourth field into the contract, which would then be stored on the chain. But this is slightly wasteful because once the contract has been deployed, this is not going to change. So we're just storing a constant in the chain, and we pay for it. So because you pay for storage on the chain. So let's not do that. Let's instead add it to the class, the Python class. Okay. And as you see here, also this is not the sp.if, but it is the if. So we distinguish the smart pi if from the Python if. So now we have the Python if, and then here I'm going to specify misère equals true. Okay, and let me compile this. Yes, so if you look at this line, you can see that, so the sp if done value, these correspond on the left and the right. And then the next line, it only shows you the first case of this if statement, right? We don't have this winner equals sp sender here. So this means once the contract is in the chain, we don't have this misère field anymore. We just specialize the contract to one of the two cases. So if I change this to false here, we get just what we had at the beginning, namely that we're sending it to the sender, so to the last player. So this is what we call meta-programming. So without really going into a different language or manipulating strings, anything like that, you can have Python programs that dynamically write smart contracts. So let me show you one more example.
You have
the college conjecture states that this function here, when repeatedly applied, yields a sequence that always terminates, no matter where we start. So you take a number. So there's an example here. Sorry, here's an example. We start with 12. Because 12 is an even number, you halve it. 6 is even, you halve it. 3 is odd. So then you apply this, 3n plus 1. So 3 times 3 plus 1 is 10. 10 is even, half, and so on. Okay. And there's a conjecture that this always terminates, but well, we can't actually prove it using blockchain technology, but at least we can try it. So I could now just write a smart contract that, well, just has less. We have a number, and I'm sorry, there are 3 minutes, you said?
You have 2 or 3 minutes left.
Okay, thank you. Okay, so let's do this very quickly. So I'm not just writing a loop here and that computes this function, but there are 3 contracts actually, so that communicate. Okay? So there's one contract that takes 2 parameters, okay? A callback, which is another contract. So it has one entry point that takes a callback contract and an integer, and it will call back the callback contract with the half of that number. And then we have the same thing for odd, which calls back with 3n plus 1. Then, so we don't have time to look at this into detail, but then there's the main contract, the college contract, that receives any number. This looks whether it is even or odd, and depending on this, calls either the on-even or the on-odd contract. I just want to show you, after deploying this to the chain, what it looks like. So I have a example of that. And then I just computed this morning. So let's explore this. Okay, so the counter is 9. So we started with 12 here. And 12 takes 9 steps to go to 1. And here you can see the operations. So let's start from the bottom. We started with 12. This leads to an outbound operation. So this is a contract calling another contract. Okay. And then we get an inbound operation again from the contract calling us back, and so on and so forth. All right. We're running out of time. Let me just show you one feature that is that we're currently working on is decompilation. So with this Explorer, you can go to any contract written in SmartPy or not, in Lego or Michelson or whatever. Then, of course, you can look at the Michelson code. You get these annotations here, which make it more readable, but, well, it's still quite difficult to read. So what we like to have in the future is something like this. You just click on SmartPy, and it gives you a decompiled version of the contract. So, well, this is friendly syntax. It's still a bit clumsy and doesn't work in many cases, so that's why this is not public yet, but that's sort of what we're aiming for. All right, let me briefly conclude. Well, you can go to our website to try it out. Things are still evolving, of course. You can go to the website or use the command line interface. There's a vibrant community of users on Telegram and the Slack exchange mostly. So here are the addresses. Please join us. And Michelle told me there was a question from YouTube about how many people are working on SmartPy. So depending on how you count, between well, we have 3 or 4, and none of us works on this full time, which is interesting. But anyway, so thank you.
Okay, thank you, Roland. Thanks a lot for this presentation and live demo. Maybe questions in the room? Yes.
Hello. So I want to ask two fast questions. The first one is, can we import native Python packages to SmartPy? And if yes, which ones? The second question is, can we implement or develop a smart contract that deploy dynamically smart contract notion of factory? That's it.
I see. Okay, so the first question, can we import any Python library and package into SmartPy? The answer is yes, but this does not mean that you can use any package on the chain, right? So this is again to do with metaprogramming. So you have the program that writes your contract can use NumPy or whatnot. But once you're on the chain, of course, you're limited to the SmartPy language, which reflects the constraints of the Mikkelsen language.
Yeah, Roland, if you could unshare your screen, we could see your face, and that would be slightly better. Thank you. Yes, great.
Okay.
So
did I answer your first question?
So can you first mention which packages can we import, or because I searched for that in your documentation and I didn't find anything.
Oh, I see. Okay, the slightly more technical answer is if you're doing it in the web browser, you have the packages that are that come with a package called Brighton, which is a Python simulator that runs in your web browser. So this is how the website works. Which, by the way, is open source. You can, if you look at our repository, you will find a directory called site, which contains the website. If you do it locally, it is indeed using your local Python installation. So I guess it depends on whatever you have there. There may be some parameters or arguments to set in order to actually do this, but yeah, if you have difficulty, please do ask on Telegram or Slack Exchange or wherever. Okay. The second question was about factories. So there is a template on the website
the multi-sig
that is called Tic-Tac-Toe Factory, if I'm not mistaken, or also the multi-sig. So this is yet another example of metaprogramming where you have one program produce several contracts depending on certain parameters.
So to introduce the question in a more simple way, can we implement an entry point in a smart contract by calling it that entry point deploy a smart contract and returns the address of new smart contract deployed?
So you can. So this is a question about Mikkelsen almost. I believe you can create new contracts. You can create new accounts, but you cannot specify the code. I don't want to say anything that is wrong. So I'm.
Okay.
Well, yeah, maybe if it goes too technical, maybe you can join the Telegram channel and ask that question in that channel.
Okay.
Yes, please do.
Any other questions? No. So thanks again, Roland. So you can see me here. Thanks. Okay.
Bonne journée.
Merci. And that's a round of applause. The next presentation is by, I had their first names. They're going to tell us about how to translate or start to translate, Madfish solution, thank you. About how to translate Solidity into Lego. So I'll let you introduce yourselves because your names, I don't have them in mind, I'm sorry.
It's okay. Can we get the presentation?
You can use that microphone.
All right. So, hello everyone. We are Madfish Solutions. Can we get the presentation? No, not yet. Sorry, maybe it's my PC, right? Just a second. Yeah.
Okay.
Okay, we got them.
Good. Thank you.
Okay. So, hello, we are Madfish Solutions, and we came all the way from Ukraine. We are a team of 3 people. I'm Julian, this is Stacy and Sergey, and we are developing Solidity to Lego Transpiler. It's an app which can help you migrate from Solidity to Lego by translating smart contract and helping you and showing you warnings where it's appropriate. Thank you, guys. I will continue by myself for now, and I wanted to start from the question like how many people here know Solidity? All right, this presentation is directed towards people who know Solidity. It's for total beginners in Lego. And before I start to go into syntax, I want to tell you about why another smart contract language needs to exist and why Tezos uses it. So Solidity is for sure not supported in Tezos because of Michelson. It's an underlying language, low-level language of Tezos. In a way, Michelson is Tezos EVM, but not right. Lego to Michelson is like Solidity to EVM, so Lego is being compiled to Michelson, and both Lego and Michelson has some advantages over Solidity. So EVM is low-level virtual machine, and high-level languages like Solidity are being transpiled to EVM assembly language. Michelson is Turing-complete language as well, but it's not a virtual machine. It is more like a separate language which gets interpreted by Tezos virtual machine, and it combines both low-level and high-level features. So on low level, it operates on stack, just like Bitcoin or Ethereum, but it has no named variables or functions. And the high-level features include statically typed and purely functional. The language itself is purely functional. And it provides collections like maps, sets, and also it has crypto functions like EVM does, for example, SHA-256 or Blake2B. What does it mean for a language to be purely functional? Pure function is a function which where return value is determined only by arguments of the inputs. And pure function doesn't produce any observable side effects. No instruction modifies existing element on the stack, and it only adds or removes elements. Michelson program by itself is a whole pure function, and pure functions have a lot of advantages for common languages, for common programming. Pure functions can be memoized, they can be optimized by compiler effectively, and can lead to greater parallelization. But for smart contracts, the most valuable property is ease of reasoning. So we can have great tools which help us to reason about code because of pure functions. So what is formal verification? Formal verification, it's an act of proving correctness of application with some respect to some specification using mathematics. And the formal verification originated from industries where it needed the most. It is aerospace, medical, nuclear industries, where people's lives are at stake. But in blockchain industry, it is also super useful because we can verify that funds are not stolen, that keys are not transferred, and no funds created out of thin air or destroyed, for example. And unlike usual testing, formal verification is exhaustive. It can prove everything, that the code written is totally according to the specification, but specification may have some errors as well. So it is not a 100% guarantee. So how Mikkelson helps us and how does it compare to EVM? EVM is a virtual machine and it stores low-level code on blockchain. We store low-level code on blockchain on Ethereum. And this code being submitted to the blockchain is extremely difficult to analyze. Solidity compiler by itself doesn't have any certification, so it is also difficult to decompile the code. There are some advancements in this area, like intermediate language named Yule, but Mikkelson prioritizes the verification over efficiency from day one. And you may think like validity maybe is not deal breaker. Solidity and Ethereum exist for a few years, but Tezos' stance on this is that hacks and stolen funds are hurting reputation of Tezos ecosystem as a whole. So Mikkelson has two formally verified implementations, and one in COC and one in F***. And right now, if I'm not mistaken, OCaml version is used on production, and it only has type soundness verified for this implementation. But I think we will have sometime soon a proven version on production. So how Solidity compares to LEGO in that regard? So Solidity is imperative object-oriented language. It's somewhat similar to JavaScript. While LEGO is a functional language, it is influenced by OCaml. And LEGO is intentionally keep tight on features, so it is simple, so there is no subtle complexity. And it is easier to reason about LEGO in total. And it is still Turing-complete language. It is capable of almost everything that can be done in Solidity. Contracts in LEGO can be formally verified, at least on Mikkelson level. And you have more fine-grained control over logic in LEGO than you have in Solidity. And it's functional if you're into that kind of thing. So yeah, now I want to introduce you LEGO syntax a little bit compared to the Solidity. And it is not that different from the Solidity on a basic level. So like math, array access, function calls, it is all present and it's all rather similar. But the paradigm is different. So as I said before, LEGO is functional. And there is OCaml influence. So you have, for example, such quirks like if is always followed by else, and you have to put skip operation if there is no else clause. Or for example, uint is being called net. It comes from natural. It means natural number, basically unsigned. So somewhat different variable declaration. And you have to enclose your imperative statements into blocks. If someone is familiar with Haskell, it's similar to do notation. And for example, with keyword is something similar to return in Solidity. So I want to show you the function declaration and compare it. All right, so on the top we have Solidity function, as you see, and on the bottom a LEGO function. And as you see, function is the same keyword here. The name is also following the word function. In Solidity, we have types preceding the name of the argument and comma between arguments, and we have modifiers following them, and then we show what we return. And the one statement inside that, you can see we return true. But in LEGO, we have the same keyword function for bar, but then we declare our arguments as const name and then type after colon, and separate arguments by semicolon. And return type is also written after colon. And you will have then block of your code, and with is keyword to show that what you want to return from this function. And as you can see, true word is also written from the uppercase letter. You have similar constructions to mappings and arrays. So you can compare them. You have mapping from address to uint 256 in Solidity, and the same thing in Lego. But it maps address to net, its natural number. The same thing with arrays is roughly translated like this. You see your in Lego var nums list, and then you specify type. And after that, you declare your list right in this place. All right, so there is a big difference between how a smart contract is abstracted in both these languages. So in Solidity, basically what you have is your sol file, and you have your contract keyword, which specifies what is a contract. But in Lego, you have Lego file, and there should be a special function named main, and this function have to be defined in a specific way. So this is, for example, our declaration of smart contract in Solidity. I think you're all familiar with that. But this is a scheme of the function which defines a smart contract in Lego. So you will have to declare your input parameter and current state as an inputs to your main function, and you have to return two arguments. It's a following transaction, so to say, and the new state of your contract. So here is a contract skeleton. This is one function only for this example, and you can see we are accepting two arguments. One argument is input, and the second argument is our previous state. And we are returning two arguments as list of operation and our new state. And here we see declared as types. And after that, after keyword with, we're returning them as values. This thing as a bottom line that nil list of operation basically means empty array. I will explain later in detail what does it mean. So I want to highlight some syntactic differences in these two languages, which I found difficult to understand at a glance when I first started writing in Lego. So these are tuples, and the declaration or returning them is similar to Solidity or any functional language, but declaration tuple type is a bit different. It's written using the asterisk. As you can see on the second row, you have your foo type, and then asterisks and bar type. And there is an example of returning, and you can see that we define return type as foo type asterisk bar type, but return them using with foo, comma, bar. Right, the next great feature of Lego that I like, but Solidity doesn't have it in the same way. So it's enumeration called enum. In Lego it's called variant type, and Christian and Remy talked about it, but I will repeat this as well so you can compare it to Solidity. So it's a simplest case. You can see on the right side that we have an enum coin, and it has a head and a tail. It's two values. In Lego, this is declared as type coin is, and then you write head and this line and the tail. And if you want to use this enum, you can, in Solidity, you write coin, so it's a type of enum, then name of a variable, and then type of enum dot head. When in Lego, you write const head, colon, type, and then head without namespace in it. But there is even better usage for this variant type. Solidity doesn't quite have this feature implemented, but I have tried to imagine it. On the right side, you can see some kind of imaginary Solidity. Basically, the idea here is that we can attach a payload to an enum value, and you can see that user is divided to admin, manager, guest, and it has int attached, let it be ID, for example, ID of this user, and it is attached to the key of the enum. And in the Lego case, it is a variant type, and it basically wraps this ID around the type. And usage, and once again, it's imaginary usage in Solidity, but let's better focus on Lego usage. So you declare your user, for example, and the admin, and in the parentheses you write the value, like it's the ID of this specific user. Pattern matching is a way how you use these advanced enums, also called variant types. You write case, and then you specify the key of the case, and this thing in parentheses, you can see to the right side, admin in parentheses ID. Oh, sorry, it's getting translated to the right side, and you can use it at the right side. You can see how for the manager case, I sum ID plus 1000, and that's a neat feature. All right, the next thing is kind of difficult. I will try to explain it to you, but I'm not sure how it will go. But anyway, I hope Stacy will later explain how it works in real cases. But multiple entry points is a difficult case in Lego. In Solidity, it's pretty simple. So you just find the ABI, you form arguments properly, and you perform the call. There is no much hassle in Solidity for this case. But in Lego, we have our contract as a singular function. So how do we call another function in this contract? There is a pattern called router, and this pattern leverages this dark magic of variant types and pattern matching to achieve like multiple entry points to our contract. So let's take two functions, for example. I will want you to remember them. It's add and subtract, accept into arguments, and returning like sum or result of subtraction. It's simple. Then for each of these functions, you will have to implement this variant type enclosing int as an argument. And then when you are declaring your main function, you are going to accept both arguments. And then as a return value, you will destructure this argument to get a value out of there and pass it to the function. At the same time, returning a return value of the function that you want to call from the main. You can see at the bottom of my slide, I have last two words. So like you have Lego dry run main Lego main. We specify main is the name of contract. Increment in parentheses 5 means that we pass argument 5 as the first argument to our main function named const param of type action, and then we pass the second 5 as a second argument. And if you look to the, I think it's fourth line, you have case param of increment n in bold, and this get passed to the add function. So as a result, you will get 5 plus 5 in this case. I think it's a bit complicated and it's difficult to explain, but it's a pretty neat feature. It gives you a lot of control and allows you, so as I said earlier, all this is done to simplify analysis of the contract and allow for easier formal verification, because in Ethereum formal verification is a hard problem, and in Michelson and Lego as well, it is kind of solves problem, but I think it's a lot of work has to be done on that field. And on the good news, so since we are writing Solidity to Lego transpiler, we are able to generate a router based on your Solidity code. And but you may have to specify more concretely what your function does, what is the visibility, what are the specifiers like pure view internal, so our transpiler can better understand if the function should be put to router or if it is just internal function that has to return only one value. So yeah, and also we have been working with Lego for past 3 months, and everything was improving thanks to Lego team, so it's getting simpler and simpler every day. Yeah, for the next part, I want to invite my colleague Stacy to tell you about atomic swaps. We have a real-world contract transpiled using our Sol2Lego utility, and Stacy will highlight you the best parts of that and explain how it works. Thank you.
Hi again. Let's look at our compiler in action. We prepared a real-world example that is an atomic swap. It's a smart contract that enables exchanges from one currency to another one without using any third parties or middleware. It is a really awesome example as it contains a variety of types, functions with different mutability, structures, and enumerations. Let's start with structures. We need structure swap, which contains information about exact swap. Time lock is time until the swap, until the value is locked on this contract. As a trader is someone who sends this money. Withdrawal trader, the guy who receives this money. Secret lock is a hash of secret key, and that one who provides the secret key will receive money. So in compiled version, we receive type records that has all fields from the original contract with transpiled types. That means uint becomes not, addresses remains addresses, and bytes with different lengths becomes bytes. Solidity has such a thing like default values. And when you declare a variable without setting its value, it gets a default value. So for structures, we need in LEGO define this default value by setting each of its fields to our imagined default values. There is such a thing in Solidity like enums that were told by Julian. And we compiled in a bit different way, not using variants. We declare constant for each subtype of the enumeration. And the default value is the 0, 1. Both LEGO and Solidity contracts has states. In our case, we have swaps and swap states. It is a mappings of structures, and in compiled version, we wraps it all in records, and that contains fields that inherits names from the original contract. We do not have events in LEGO, so we just comment it out with its names and arguments, and then developer can use this information to remove it or to change it to something else. Also, LEGO doesn't have modifiers, but we dispatch body of modifiers in functions directly, and modifiers declaration we just comment. That is the most interesting part of my speech. It is for function transpilation. You can see that the function open. It has some arguments and it returns nothing. Also, it is public payable function that has one modifier. The first line of our transpiled code is part of modifier, and then the body of the function goes. You can see that the function returns two values, operation list and modified state. And it has an extra argument, state. That is another kind of function. It is a view function that returns some values. By this reason, we need to pass an extra argument to our function, that is receiver contract. And in the last line of the function, we create an operation that sends all these values to that contract. And our function returns only oplist because it shouldn't modify state. Another function, close function, it is a function that modifies state and interacts with other contract or other user. That means we have a transfer operation in our contract, and by this reason we should create a list with operation that sends money to withdrawal. And also we should modify state, as you can see we do. Another view function. In LEGO, it has not much sense because you can get value from state directly, but in Solidity you can't derive structure from mapping and get its field. So you have transpiled version on the right side. Another function is expire. It's quite similar to close function, and the most interesting part is probably default values. Also, it was mentioned 2 times today that LEGO has only one entry point, that is main, and we should dispatch functions somehow inside of this main. For this purpose, we need such an argument as that has a router type, and it is declaration over this type. And we pass it to the main and dispatch its arguments to the functions. All right, but we received a compiled contract, but LEGO and Solidity are very different, so manual fixes are inevitable. Here you can see we retrieve structure from mapping, and it's too complicated for LEGO, so we should split it to few operations. And one more time, but in a different context, and one more time. And now we have fully compiled code. It is compiled code in very understandable Michelson. You can use it, test it, whatever you want. And to sum up, we have 2 stuff. It is a CLI version and web version. And probably Yulian will show web version.
You have, yes, 10 minutes?
10 minutes, all right. So I think we can show you the web version.
Microphone.
We don't have a white team, unfortunately. Huh? Yeah, so we don't have a white team, unfortunately. But I'll just quick introduction. So on the left side, you have your Solidity code. On the right side, you have a Pascal Lego. Yeah, I haven't mentioned we are transpiling to Pascal Lego dialect. And if you have some errors, they are going to be on this tab. I'm not sure if it's visible on the screen. So yeah, it's pretty simple to use. We will share the link. You have a few examples here, starting from the simplest, and then go into the real world examples. For example, you have while here, and you can see how, for example, while is getting transpiled here to Lego while, and like how this. Let me make it even larger. So how these constructions are getting transpiled. So these not equals transpiled to these, and that Lego doesn't have increment assignment, and we have to emulate it. It's not clear, but roughly the same. And if we have a return value, we return it. Yeah, so I encourage you to try it. And also the contract which Stacy told you about is an atomic swap. We have it in examples. So it's a real world atomic swap. It works. In Solidity it works for sure, but in Lego after a few fixes it works as well. And we didn't try to do atomic swap exactly, but we checked it. And after a few fixes you can try it as well. Yeah, I think that's it. I want to invite my colleagues for Q&A if you have any questions.
Sure, thanks a lot. Yes, questions.
What is the most used Lego language? Pascal Lego or Reason Lego? Or the most used?
I'm not sure. When we started from when Pascal Lego was, I think, is the only variant, and Camel Lego was not as developed. But right now, I'm not sure.
That might be a question to the Lego team.
Yeah, it is.
We don't really know.
Okay.
We have some feedback. Okay, we do have feedback from some people who tried one or other variant, but We don't know how many of them are using such and such variant.
Okay. So your transpiler is transpiled in Pascal Lego, right?
Yeah, it is to Pascal Lego right
Thank
now.
you.
I think it's because it's the most friendly. It is the most similar to Solidity. That's the reason.
May I? Because I mentioned that in my own talk, that we are going to do transpilation between different front ends of Lego. So you won't be stuck in Pascal Lego if you don't like it. So their work is going to be reusable in Cameligo or Reason Lego or whatever front end comes next.
Okay, thank you.
Thank you. Other questions? No? Well, thanks again to the Matfish Solution team. So this is the end of the morning session. We start again at 2 p.m. There is some food outside, maybe in 5 minutes. So we have 5 minutes to chat, to discuss together. See you in 1.5 hours. Thanks.
Ça s'est bien passé, Benjamin? Ouais, pas mal. Ouais. J'ai demandé à mon fournisseur d'accès cloud s'il pouvait monter à 1080p. Donc a priori ils l'ont mis en activation, mais c'est pas sûr que ça rentre. Ouais, mais c'est pas grave. Que ça rentre dans le live. Non, c'est pas. Ce sera pour les prochaines. Tu vois. Ouais,
Pardon, je te laisse.
Si je parle là, il m'entend? Matej, do you hear me?
Yes, I can hear you.
Good. Hi. So yeah, you can see me here, but I'm not sure you. Yeah, like this.
Can you see my screen? I'm sharing my screen.
Yes, yes. So your screen is perfect. We don't see your face. Is it what you?
Is there a way to have both?
How about now?
Yeah, that's perfect. So can you go on your? Oh yeah, we have everything, including myself, which might be a bit too much. Let me. We're trying because we had remote presentation this morning, and we didn't see the face of Roland, for instance, or Adrian was without slides, so we saw him. So we are trying to find a way to have both your face somewhere in the screen and your slides. So don't.
I can try and do this. Can you see it now?
I'm not sure you have anything specific to do.
I moved the Zoom window to the screen that I'm sharing.
Yes. No, don't. Yeah, don't worry. Don't worry. I think it's a matter of maybe Benjamin who is at the. Donc, c'est.
Là, j'ai décidé que ce serait lui.
En fait, toi, tu peux. Là, le problème, c'est que t'as moi. Non, mais moi, si je disparais, le problème, c'est si quelqu'un d'autre apparaît. En fait, tu m'as arrêté ma vidéo. Ça change pas grand-chose. Non, enfin, oui, c'est dommage parce que. Okay, I'm sorry, we are speaking French.
Demander à démarrer la vidéo. Il y a peut-être un
Yeah,
truc
I'll do that. I think my video is useful because Matej, I will manage you to see the room, which is empty currently, but stay muted.
I don't know how to show my face.
Don't worry. Maybe it's the thing that you. The only thing is that when your presentation will be terminated, you don't forget to unshare your document so that you can answer questions. I mean.
I will. So I have my last slide that I didn't download.
So this would be great, Benjamin. Could you have this? I mean, could we kind of? Yeah, but if you share the document, what happens? Oh, you're sharing the desktop. Okay, which so if you go full screen on your I don't know, yeah, that would be just perfect.
Okay, I will leave it like that.
Okay, excellent.
Can you see yourself on my screen around?
No. Well, you don't. I don't need to be. Yeah. I think that the top right is the best. Like this, like this, like this, it would be just perfect. Okay. And could you go through a few of your slides just to make sure that everything is fine? Yeah, that's great. Okay, perfect. Thanks a lot.
Yeah, and then I will be switching to the editor. So top right, I don't need anything in the top right corner. That's fine.
Yeah, well, don't worry. It's I mean, not a big deal. It's I think it's better, but because all this goes to YouTube.
Yeah, I'm watching it since the morning.
Yeah. So was the sound okay?
Yeah, but during the smart presentation, it was a bit quiet.
Okay. Yeah, sometimes Roland just didn't speak, so.
Yeah.
Okay. So we start in 7 minutes. Can you? Yes. Whoa, with that.
The only problem that I have is that I have some notes on the side, and it looks weird when I look on this office too.
What do you have? Say it again. You have a.
I have two screens.
Oh.
And I have my camera on one screen.
Oh,
And
it's.
I'm looking at the notes.
Well, it's not that bad because. Yeah, it's. Yeah, not a big problem, but. And can you see the room through my own? Well, don't worry. Maybe you don't need to.
It's too small, anyways. Will there be someone asking questions for the group chat?
Yes. So I mean, yeah. Okay.
My chat is open as well.
Okay. Don't worry. So let me go. No. Let me do what?
Yes.
Oui.
It's a bit quiet though.
Yeah, it's quite changing the batteries of the microphones. So. Here. Qu'est-ce qu'on a?
I'm sorry, I thought it was you talking, but I was listening to the live stream as well at the same time.
Say it again.
I had the live stream playing in the
Oh,
background.
okay.
And I thought you were asking something.
Okay, so I'm gonna get the people to make sure people come to the room. Je suis là. C'est mieux si les gens se mettent au premier rang. If you could come closer to the screen, that would be much better. Okay, and you won't be the only ones, don't worry.
Quel premier rang ici, là,
Les premiers rangs. Enfin, plutôt vers les premiers rangs. On est chiant. Hein. Ok, donc on a Matej et James Haber. Donc je vais aller le chercher. Je vais battre le rappel. Matej, James. Je sais pas ce slide. Si je vais être sur la photo, il faut que je me mette là. Oui, essayez de vous mettre plus en avant. If you come closer to the screen. Just to... Oh, yeah, I'm sorry. Je vais demander déjà de bouger, donc c'est dommage. Je pense qu'il y a des gens qui vont revenir aussi. Les gens sont partis manger au restaurant, ils vont entrer ensuite. Donc, tu dis quand on peut commencer. Là, il est 2 heures. On peut attendre 1 ou 2 minutes. So Matej, we start in something like one minute or something like that. Il faut que j'arrête de bouger, parce que le monsieur essaie de me suivre là-bas. Oui, c'est bon. Tu me donnes le top? Okay, very good. So welcome back to the Tezos Developers Day in Paris 2020. We are starting the afternoon session with the first presentation by Matej Sima, who will be given the presentation remotely for I don't know where, but he will tell us. It's about implementing a mini token contract with on-chain callbacks. Matej, it's to you.
All right, so hello everyone. I'm presenting from Bratislava, Slovakia, from my humble little office. And just to introduce myself real quick, so my name is Matej Sima. I'm a software engineer at a company called Stone Labs. We do smart contract engineering, tooling, and other cool stuff based on Tezos and other blockchains. Today I'm going to be talking about how you can implement a small token contract with some cool callback features directly on the chain, and it's going to follow the TZ12 proposal standard. You can find some links below. If you want to reach out at any point in time, please do, either using Telegram or on the YouTube live chat. If you have any questions during the presentations, I'd be happy to answer them. During the presentation, there's going to be a few QR codes, so please have your phones ready. If you want to check out some cool links, just scan the QR code and you should be good to go. Just a second. All right, so before we get into actual programming, I want to talk a bit more about why we will be programming the things that we will be doing today. The reason why we're doing a token contract on Tezos is because we are working on a project called the Tezos Hand. The Tezos Hand is a blockchain game that started originally on Bitcoin. The name was Satoshi's Treasure Hunt. So what we're doing together with the Satoshi Treasure Hunt team, we are porting the game to Tezos with the price of $1 million US, of course, in XTZ, right? So the game on Bitcoin was based around Shamir secret sharing or Shamir secret splits. And essentially it meant that you had a clue that you had to solve, and as a result of the clue, you received a portion of the private key, which was the Shamir secret split. Once you had enough of those, you were able to create a private key that gave you access to the prize of the game. However, on Tezos, thanks to the smart contract capabilities that we have, instead of Shamir secret sharing, we will utilize NFT tokens. What that means is that you will have a clue from the authors of the game, and as a result of the clue, once you solve it, you will get a full private key, and the private key will give you access to an NFT token. So you will be able to claim ownership of the NFT token. This gives you absolute transparency and enables decentralization. And it also allows you to trade the token on the chain with other players. So your token, for example, could be worth a fraction of the price. So it could be worth $10, but you found it. So you can now decide to sell it to someone else using an escrow service on the chain or an exchange or whatever else. So that's the cool part about the game on Tezos. Of course, there's also the price. So the game is going to be announced, I hope, soon enough. So please stay tuned and follow our Twitter or check out the link on the under QR code to learn more. So moving on. Again, talking about token contracts. So initially, when we started working on the Tezos hand, we built our own NFT token. We called it a standard, but it wasn't really a standard. It was inspired by ERC 721. As a follow-up from that, or the natural next step, was the TZIP 12, or the Tezos Improvement Proposal number 12, proposed by Tocqueville Group. So it's a standard that describes a common interface for a token contract that can store multiple tokens at the same instance. It can store fungible, non-fungible, transferable, non-transferable, or any kinds of tokens that you would like to have. So that's TZIP 12. It's a token standard. The exercise that, or the live demo that I would like to do today, will show you what kinds of tools we are using to develop those contracts and how can you start developing smart contracts on Tezos yourself. So we will be implementing a smart contract that follows the TZIP 12 interface definition. So it has the same functions with the same type signatures, parameters, and return types. And we will also be testing it, deploying it, setting up a local chain, etc. So at this point, I'm going to stop the presentation and I'm going to open up my terminal. And we're going to start by cloning this repository. I'm not expecting anyone to follow step by step, right? Because you don't have your computers with you right now. But once you get home, there's going to be a link at the end of the presentation where it will link you to a Medium tutorial where you can follow these tutorials step by step yourself. So I'm just going to start by cloning what we call a starter kit repository. So let's just do that. And we'll do git clone. There's a starter kit. Open it up. And open up Visual Studio Code. That's the editor of my choice. I'm just going to do this. Yep. And on the right side, we can see the project structure. It's quite simple. The whole starter kit is built around Truffle. Truffle is a testing / deployment smart contract development suite done by the Truffle team. And recently, they have released a version for Tezos as well. So we're going to be using that. So just let's hide the unnecessary stuff. Open up the terminal. And the first thing that you need to do once you clone the repository is you have to install dependencies. So let's just do that. While the dependencies are installed, you will also need Docker, which is fairly common nowadays. So you need it running. We already have that. And Node.js, of course, to run the tests, install the dependencies, and all the other cool stuff that you might be doing. So we wait for the dependencies to install. Should be done. Yeah, there we go. Clear up the terminal. Okay, so what the starter kit gives you is an example contract that follows the TZ12 spec. It only implements a very simple subset of the features available in TZ12. So first thing we can take a look at is what kind of data the contract is storing. We can do that by opening the storage file right here. So we see that the storage type for the contract is or are token balances. And above we can see that token balances are a big map between token owners and token balances, where the balance itself is a natural number and the token owner is always an address or a public key hash in Tezos, right? So it's a Tezos address and the balance. So it's essentially a very simple ledger between addresses and their balances. So the only feature that is implemented in this contract is the ability to transfer tokens from one address to another. We can check out the transfer implementation here. I hope you can see the code well enough. If not, please let me know. So this is how the transfer function is implemented. It's really, really simple. It checks or it gives you the permission to transfer only your tokens. That's line number 9. Otherwise, it fails. And then it updates the balances if you have sufficient balance. And that's about it for the transfer. The important thing, when we talk about TZ12 and the transfer is to be coherent with the standard parameters. We can check that out in a separate file, which is called the transfer param. And here we can see the type signature of the transfer parameter itself. And we can see that I think it's a good idea to read the types from bottom to the top, because it gives you a good idea of what the developer was thinking when he wrote the types. So the transfer parameter is a list of transfers. That's how it's defined in the TZ12 interface. And the transfer itself is you specify the token ID that you want to transfer. Token IDs being natural numbers. That is, again, part of the standard. Then you specify the amount that you want to transfer. Again, we saw the definition in the storage file. And you specify from whom to whom you want to transfer the tokens. So this is already a huge, important part of TZ12, that you have a contract that has a transfer function that supports exactly those parameters. So this is what you get out of the box when you clone the starter kit. So there's a couple other things that come in with the starter kit as well. Probably the most important, at least from my point of view, is the ability to have a local sandbox network where you can implement stuff. Of course, using the starter kit and using Truffle, you can connect to the testnet, mainnet, or whatever network that you want. We can start by, for example, compiling the contract to see if it compiles. So let's open up the terminal, put it to full screen, and we will do npm run compile, and we will pray that it will work. Yeah, running Truffle compile for us, compiling our contracts, using the main entry point, whatever. All right, so the contract compiles out of the box. That means our stack is good to go, and we can try some more advanced stuff. So just to recapitulate, we have a starter kit set up with a simple contract implemented. Maybe we can take a look at the folder structure as well. So you have a contracts folder, you have a TZ12 tutorial contract here, and then some other files like what we've seen, the storage, the transfer param, the transfer function itself, and some other files that we don't care about right now. So that's the folder structure and the contract structure. The next thing we want to do is we want to run the test suite that comes in with the starter kit. To do that, we first need to start the sandbox network, and you can do that by the following command. Let's kill a sandbox first, in case there's one running. Okay, killing sandbox, okay. And you can also start a sandbox. That's pretty obvious. And the last parameter for this command is the protocol that you want to activate. So you can either activate the latest protocol, which is Carthage, or you can activate Babylon, which is also supported. However, I doubt anyone or any network will be running on Babylon at this moment, since Carthage is live right now on the mainnet. So we can start a sandbox. This will allow us to run the tests or the migrations that we have defined in the starter kit. So the sandbox is being started in Docker, and a call to the RPC is being made to see if the node has already started or not. So the node is started, we can proceed. And we will proceed by running a simple test suite that comes with the starter kit. So npm run test does it for us. And now we wait. All right, so the contract is already compiled. We did that before. Using network development, that means that there's a pre-configured network that is being used, and that is on localhost at port 8732, I think, and that's where your local sandbox node is running. This is also important for other external tools that we will be using later in the tutorial, that we have this accessible with cores properly configured at this given port on localhost. So now we wait, it should be rather quick. There we go, the tests are already running. We see that our contract is being deployed at the following address, and some of the tests have already finished. Now all of them have finished. So we see a bunch of really simple tests. There's 5 of them. So first of all, there's reading of the storage, then 2 transfer tests, and that's about it. So before we open up the test suite, maybe we should talk a bit more about how the contracts are deployed within Truffle. So that is being done through what is called a migration. If you are familiar with, let's say, web backend development, a migration is where you have a database, let's say, in some state, and you apply the migration to change the state of the database. And what it means here is that you take a contract and you deploy it to the chain. So it's a fancy name for deployments. Let's open up the migration file for our contract. So we have seen the storage of the contract, and we know that the storage is just the map between addresses and balances. So in order to deploy the contract, we need to define the initial storage value, which is done right here. So we know that Alice will hold 10 tokens. And we say deployer, deploy sources that we have, that is our contract, and the initial storage. So as a result of this deployment script, we will have a contract deployed at a certain address where Alice will own 10 tokens. This is also important because our test suite will depend on the initial state of the contract. The tests can be also found in a separate file over here. And we can take a look, for example, at transfer tests. That's an interesting test to look at. So here we see a test. It should transfer 1 token from Alice to Bob. So Alice and Bob are just addresses in our testing suite that are funded on the sandbox chain. So the first thing that we do in our test suite, those are the tests that we have run previously, is that we create a parameter for the entry point that we want to call, which is the transfer. We know based on the type signature that it is a list of transfers. So we have an array of objects. So array is a list, and the object is the transfer itself or the legal record. The token ID will be 0 because our storage is too simple to support multiple tokens as the TZIP specs allows. The amount will be 1. We are transferring a single token, and then we provide the addresses. So from Alice to Bob, because we have initiated the contract with Alice owning 10 tokens. So Alice should be able to transfer at least 1 or more to Bob. Then we call the entry point using Taquito. So we await for the result of the transfer call. And then we check the storage of the contract, and we ask for the balance of Bob. So Bob's public key hash should have a balance, and we expect it to be 1. This is obviously true. The test suite passes. So this is how you do tests in the Truffle suite. There's obviously more tests that you can look at. You can see all of this once you clone the repository. So we can go back to the presentation, I think. Let me just do that. Yeah, all right. So we've seen how the starter kit looks like, how the initial TZIP12 contract looks like, how it is tested, and how it is deployed. Now, the next step will be adding a feature to the existing contract that is also specified in the TZIP12 spec. So there's a feature called balance off. We will not yet be implementing it, but we will be discussing how it's implemented and why it's implemented that way. So the TZIP12 contract lives on chain. You can see it on the right side here. And it holds the ledger of balances for addresses and their balances, right? So if somebody wants to read the balance, you can do it using JavaScript and the RPC like we did in our test. However, if another contract on-chain wants to read the balances from our TZIP12 contract, the contract is not able to use the RPC. That's obvious, right? So there has to be a way for any third-party contracts to read the balances. That's why we have an entry point called balance off. It accepts a list of balance requests. So you specify, I want to know the balance for this token ID and this token owner pair. And it specifies a callback address that the TZIP12 contract can call. So we can see the lifecycle on the graph down below. So somebody, let's say a user or the test suite, says that I want to request the balance. It tells it to the third-party contract. The third-party contract calls balance off on our contract. And then our contract calls the callback and gives the information to the third-party contract. So I hope that this is clear enough. If there are any questions about the lifecycle, then it's probably best if you ask now. Otherwise, it might be too confusing when we implement this stuff. So, Michel, are there any questions?
Yes.
Okay.
I wonder, does this happen in the same transaction? Sorry.
Can you please repeat the question?
I was wondering, does this happen in the same transaction?
So on Tezos, when we talk about transactions, we should also talk about operations. I believe, or at least in my understanding, this happens in one operation. And the transactions are internal. So you see the person on the left side or the test suite? That is someone who initiates the operation by sending a transaction to some contract. This contract then internally talks to TZIP12, and then TZIP12 again internally on the chain sends an internal transaction back here. But all of those transactions should be wrapped in the same operation hash. And we will also see this at the end with some debugging tools that the operation hash should include all of those transactions. So one large operation, including small transactions. Does that answer your question? Yes? Okay. Yes. So, all right. Any more questions?
I think no. You can go on.
All right. So just to recap again, balance of entry point exists on the TZIP12 contract. It accepts a list of balance requests, so pairs of token IDs and token owners or addresses, and returns back in a callback a response with token ID, token owner, and the balance for the token owner and the token ID. So that's the lifecycle, that's the loop. And you can imagine the third-party contract to be, let's say, an exchange, and the exchange wants to know if you have sufficient balance to I don't know, to open up a trading position or whatever, right? So the exchange would ask the TZIP12 contract for your balance, for example. As part of the tutorial, the written one on Medium, you would be allowed to, you would be able to follow the tutorial step by step. However, I will cheat a little and I will jump to a finished version and I will walk you through the source code instead. So I'm just going to clone the resulting repository. And we can start here. Okay, git clone. Okay, close this. All right, so the resulting repository is based on the starter kit, and it already includes the implementation of balance off that we want to have. But let's walk through how you would implement the balance of yourself and how the code will be split, why would we implement it in such a way, etc. So the first thing that we should probably check out is the type signature for the entry point itself. We should be able to find it in the following file. So balance of param, right? So this is, let's again start from the bottom. I hope you can read it well. So we know that the balance of entry point accepts a list of balance requests. So we see that here, list of balance requests. And it also accepts a callback. We see that down here. And the callback is a contract that accepts the callback parameters. And the callback parameters is again a list of balance responses. So going up here, a list of balance responses and requests. The balance request is again a record, as we said, basically a pair between owner, which is the address, and the token ID. And the response is the balance request plus the actual balance from the contract storage. So that's the type signature of the balance of entry point, and also the type signature for the lifecycle contract receiving the result. The next thing we should take a look at is the actual implementation of the balance of entry point. So let's open it up. Zoom out a little. Okay. So the balance of entry point takes the balance of parameter and the storage. You've seen this in talks earlier, how the type signature of a legal entry point should look like. So this is exactly it. And the next thing that happens is that we have an iterator function that goes through the list of requests that we have, and it populates the balance from the storage. So it looks for the owner in the storage and returns the balance or the default balance, which is always 0, and transforms that into the balance response object or a record. So we have that here in the iterator function, and we call that in a list map. That's quite straightforward down here. The interesting part comes when we want to send back those data to the contract that called balance off. We do that by forging an internal transaction that is parameterized by the balance of callback parameter, which is the list of balance of responses. And the operation or the transaction will be sent to the callback contract, which we received in the parameter here. And we return it as a list of operations, and that's the whole magic. There's not much more to it. The tricky part now comes when you want to test the balance of entry point, right? Because in the test suite, you're basically off chain. You are not a smart contract when you run the test suite. So there's no real way to confirm that the returned operation sent back the data that it should have, and there's also no contract that we could pass that would accept the callback parameters. This can be solved in a very easy way by implementing a mock contract that will first of all invoke the balance of entry point, and that will receive the data from the balance of entry point. I call this the balance requester. We can take a look at it as well. So it should be down here, contract main balance requester, right? And we can take a look at, for example, what kind of data the balance requester will store. The storage is really simple. It will only store a list of the responses received from balance off. The actions or the entry points available on the contract will be the following. One will be to request balance. That is something that we will call from our tests. And another one will be receive balance. That will be used as a callback from balance off. We can also take a look at the implementation of the request balance that only exists for the testing purposes. So the first thing that it does, it calls the contract, the TZ12 contract, and it asks for the balance of entry point and sends a bunch of params that we specify, and then sends that as an operation, and that's more or less it. So we have balance of implemented. We have a contract that will request the balance from the TZ12 contract. So we can write our test suite. But before we write the test suite, we need to write the migration. So let's take a look at that. Migrations, right? So we had the migration for the TZ12 contract itself. That stays as it is. Alice still has 10 tokens. The second migration we need to write is for the balance requester, because for the test suite, we need to deploy it on the chain. The migration is really, really simple. Require the compile contract, set the initial storage to an empty list or an array, and deploy it. So in the test suite, we will have two contracts deployed on the sandbox chain, the TZ12 contract and the example balance requester contract, with the initial storages specified in the migrations. So assuming we are happy with the way it's implemented, we can start writing a test suite in order to verify our implementation. So let's take a look at the test suite here, and we will scroll down to where the balance off is being tested. All right, so this would be the test. So what happens in the test, we can maybe go back to the presentation and take a look at the lifecycle diagram again. Yeah. So what you see in this graph down here is what needs to happen in the test. So the test suite requests balance from the balance requester. The balance requester requests the balance using balance off from the TZ12 contract, and the TZ12 contract calls the callback provided, which will be receive balance, back on our balance requester contract. Then the test suite can take a look at the storage of the balance requester contract and verify that the data that has arrived from the TZ12 contract is correct. So maybe another room for questions before I proceed with the test suite. So are there any questions?
Questions? Nope. Everything is clear.
No. All right. So I hope that's a good sign. Starting with the test. So first of all, we have to put together a list of balance requests. So we have, again, an array of objects where the owner is Alice and the token ID is 0, right? Because we don't have multiple tokens, we have just one because of how the storage is limited in our contract. So this means that we want to know the balance of Alice, which should be 10 based on our migration, right? So, and we also know that the TZ12 contract lives at a certain address because we have this deployed using our migrations, so we can access that in our test suite. So the balance request and the TZ12 contract address are two important things. We pass those to the request balance entry point on our mock contract, and we wait for the result. And once the entire loop is finished, we can take a look at the storage of the balance requester, get the deployed balance for Alice. So we go to the actual TZ12 contract and we ask for the balance through the RPC, so of the chain, go to the RPC, get the balance, and then compare it to what we have received in the balance of loop. And it should be the same. So we do an assertion. And And if everything is implemented as it should be, this test should pass. So we can go ahead and run the test suite. Also keep in mind that we still have the sandbox up and running, so we can run the test. How much time do we have left?
10 minutes, including questions.
Okay, thank you. So we run tests, the contracts get compiled for us, right? Because we haven't compiled the contracts in this repository or in this project yet. So the contracts have been compiled, and now we wait for the test suite to run. Okay, so the tests are running, and we can see that we have now 2 contracts, not just one, deployed at their addresses. So the output of the addresses is really important because in a minute we will go to an external debugging tool called Better Call Dev, and we will use that to additionally verify if everything works as it should. So right now the test suite is passing. It can only mean 2 things. The positive scenario would be that everything works as it should, and the negative scenario would be that the test suite is probably not written correctly, right? I can assure you that the test suite is written correctly and it works as it should, but you don't have to trust me. You can try it yourself. But just to verify visually, outside of the test suite, we can use the debugging tool that I have just mentioned. So we can copy the address and open our browser. So we'll open up Chrome. We will go to Better Call Dev. We will select the sandbox mode. This will automatically talk to our local host RPC node. We can paste in the address of the contract. We wait for it to load, and there we go. So if you scroll down, you can see that the contract has been originated at some point. You can see the operation hash, you can see the costs, the gas that has been spent, etc. And you can also see the time, blah, blah, blah. So, but the thing that is interesting for us is the balance of life cycle, right? So this is which contract? Hold on, I forgot. So it's the balance requester, right? That's what we're looking at right now. So we see that someone has called request balance. That's the first thing that we see. And we see that there has been an internal transaction from the balancer, from the balance requester contract to the TZIP12 contract. This is the address. We can maybe verify it again. So M2 at the end is the TZIP12 contract. So balance requester calls the TZIP12. We can see the internal transaction here. And then again, internal transaction from the TZIP12 to our contract at the receive balance entry point. And we can see the parameters that have been passed. So starting at the top level, we are saying that we want to use the contract, the TZIP12 contract at this address. And those are the requests. So we want to know the balance for Alice, for the token ID 0. And the response is token ID 0, owner Alice, balance 9. Because previously in our test suites, we have also transferred 1 token from Alice to Bob. So the resulting balance is not 10, but 9, which is correct. And we also see the storage update for the contract. So this basically gives you a sort of a visual idea or a way to debug the contract that you have written. Just for fun, we can go to the TZIP12 contract and take a look at the operations there as well. Also, to answer the first question from the talk, you can see the operation hash here at the top, and you can see that it is the same here on one contract and also the same here on the second contract. So it all stays within the same operation. So right now we're looking at that TZIP12 contract, and we can see that there has been a transaction from the balance requester to the TZIP12 contract. Balance of has been called with those parameters, and then there has been a response. So that basically concludes the tutorial. I hope that you have learned something and got some inspiration. You can find the full tutorial if you scan this QR code. It will give you a link to Medium where you can walk step by step with screenshots through the same talk that I gave right now. That's it. Thank you for listening.
Okay, thank you, Matej. Any question? No? One more question? Yes.
Do you think this can be a solution to the update of the contract, splitting in a functionality contract and allow it to be updatable? And this may
So you're talking about the file split or the testing?
I'm talking about the use case of this callback.
Oh, okay. So I think that, you know, we don't live in an isolated world. There's going to be more developers coming to the ecosystem, and they're going to be building interesting products. And for those products to be compatible with each other, they need a way to communicate. And the balance of and callbacks is just one way how those products can communicate together. So yeah.
Okay, any more question? Nope. Thanks again, Matej.
All right, thank you. If you want to reach out, you see the link at the bottom, Twitter or Telegram. So I'll be happy to talk to you. Thank you and bye.
Thank you very much. The next presentation, did you plug your?
Not yet.
Not yet. Okay. No, you can do it. Just make sure. Can you go to the screen? Yeah. Okay.
Do I need to log into Zoom?
No, not at all. So you just need to speak in the microphone. You can take it with your hand if you prefer. Okay, as you wish. So the next speaker is James Haver, who will be telling you about Dexter, a decentralized exchange for Tezos. James.
Hi, I'm James. I work for Camel Case, and hold on one second. How do I get this to full screen? Okay, that's better. Yeah, and I've been working on Dexter. It's a decentralized exchange for Tezos. So I'm going to present this at a bit of a higher level and not assume that all of the audience knows Tezos. So if you already know these things, please bear with me. And then we're going to do a demonstration. And then I'll leave some time for questions. And if there's not questions, I'll go into the more technical side of it. And feel free to ask about the more technical side if you have any of those questions. Okay, so what is Dexter? It's a decentralized exchange for the Tezos blockchain. And what that means is an automated market maker. So let's say you have two commodities and you want to exchange one commodity for the other. What the automated market maker means is that it provides a space to do that, and it decides the price of those commodities automatically. This is modeled after Uniswap. It's a decentralized exchange on Ethereum. So a little bit about Tezos for those in the audience that don't know that are not as familiar with Tezos. It's a proof of stake blockchain that differs from Ethereum through its use of on-chain governance. So that means changes to Tezos are proposed on Tezos and decided by stakeholders of Tezos tokens if they want these changes to be implemented or not. And so the holders of these Tezos tokens, which will be referred to as XTZ through the rest of the presentation, may stake their XTZ to individuals we call bakers and earn rewards. So this part about rewards is important to keep in mind because we want to maintain the right to earn these rewards for anything that's on Dexter. So what about the smart contract language side of Tezos? So we have Michelson. It's sort of the lowest level programming language for Tezos smart contracts, and it's relatively readable for a low-level programming language. It has a lot of high-level data types and primitives, and then there's a lot of, in the ecosystem there exists languages like LIGO and Morley that compile to Michelson, so you can code in a higher-level language and output to the language that Tezos uses for smart contracts. And then before getting into Dexter directly, we need to talk about what tokens are available on Tezos. So we already mentioned XTZ. These are the native tokens of Tezos, but you can use smart contracts to create new tokens that exist in Tezos. So so these are very standards. The first one's called FA1, and it's an abstract ledger. What that means is you define a total number of tokens that exist, and you allow individuals to be sent and receive tokens. So I could create a token, I could send it to any existing Tezos address, and you could become the owner of those, and then you can send those as you please. Then there's FA 1.2. This is a slight, let's say, improvement of FA1. FA 1.2 has the same features, plus it has an approvable system in it. So basically, I can give permissions to third parties to use my tokens as I see, and I can take away those permissions. So if you are familiar with Ethereum, this is very similar to ERC20. And then finally, there's an upcoming token standard called FA2, and it's a work in progress. It is a multi-asset interface. So what does multi-asset mean? It means a single contract can have multiple tokens that exist on it, and these tokens can be of different kinds. They can be fungible. Fungible means each token is the same and interchangeable, and they could be non-fungible. Each token is unique. Think something like Magic the Gathering or Pokemon. These are sort of gaming things that you can create on blockchains. These can all be supported in FA2, and it also allows people to design their own permission systems. So you can come up with some more abstract thing that just gives you more control. Anyway, we'll get to that a bit later. So let's take a quick glance at what Dexter looks like so you can get a better idea of what I'm talking about. So here's the user interface. You can see there's two tokens. There's these XTZ. There's this TZG, Tezos Gold. These are just things we've made up. And it gives you the option to trade these tokens and put these tokens on the exchange and remove them. So I'm going to talk a little bit more about Dexter, and then we'll get into the actual demo. So Dexter is actually two things. It's a contract and it's a web front end. So on the contract side, it's an open source Tezos smart contract that provides a decentralized exchange for FA 1.2 tokens. Or rather, you can exchange your XTZ for FA 1.2. Now, how do these XTZ and FA 1.2 get there? So we have to have pools of these things. We call them liquidity pools. So it means there's a certain amount of XTZ and a certain amount of FA 1.2 that exists in the contract. So token owners are incentivized to put their tokens, XTZ and FA 1.2 tokens in the exchange via transaction fees. So each time someone goes to buy one of these tokens, the entire exchange will take a small transaction fee. Now, this transaction fee does not belong to the contract. It does not belong to Camel Case or whoever originates the contract. It belongs to the people that have provided these fees. So how do you get these fees? Well, when you placed XTZ or FA 1.2 on a token on an exchange, you're given what we call a liquidity token that represents your ownership of the entire pool of tokens on the Dexter. So then you can get rid of those tokens, however many you like, and then you will be rewarded a certain amount of XTZ in FA 1.2. How much you get of each of those depends on the exchange rate and also how many transactions have occurred. So if lots of transactions have occurred, you will have increased the amount of this balance of FA 1.2 and XTZ that you get. And also, there's the potential to earn baking rewards from any XTZ that you've placed on the Dexter contract. And we'll get into the details about that a little bit later. So on the website, it's an open source front end that anyone can host. It allows a user-friendly way to interact with the Dexter smart contract. So if you like, you could interact with these via the command line, but it's not very user-friendly. However, for things you want to automate, that definitely makes sense. And it uses some web wallet software. Right now, what we have implemented uses Tezbridge. There's another one in development called Beacon that we're going to support. If you're familiar with Ethereum, there's a Chrome extension called MetaMask. Beacon is similar to that. And what these wallets do is they help you interact with the Tezos node and sign transactions to the Tezos node that interact with the Dexter exchange. And to run this front end, it actually does not communicate to a separate back-end server. We're not saving any of your data. All this is doing is communicating with the Tezos node and the wallet software. So I think now let's go to a quick demo so it can be a little bit more clear what I'm talking about. Okay, so this is from our website. This is Dexter. This is running on BabylonNet, and you can actually access it if you want. It's not super user-friendly yet, but we're working on it. So the first thing it asks you to do is to connect to a wallet. And when you click Connect to Wallet, it opens up a new tab for Tezbridge. So Tezbridge has its own way of managing your public and private keys. You can do that manually by putting your private key, which I don't recommend unless you are just doing test development on BabylonNet or Carthage. You can also use a ledger. Anyway, I have a few accounts set up here, so let's log into one. So I log into Alice. I'm going to use Alice as a signer. And now I go back to Dexter. So I've logged in, and you can see that I'm on the swap screen. I have a certain amount of XTZ. Let me zoom in so it's a little clearer. So Alice has 1,500 XTZ. She has 790,000 Tezos gold. And below you'll see how much the exchange has of each of those. So let's say I want to sell some of my XTZ and get some gold. So the current exchange rate is 1 XTZ to about 42 Tezos gold. It rounds down a bit for that transaction fee. And so then I click here. Tezbridge is asking me to okay a request from Dexter, so I can test it before deciding if I want to do this trade. So this will clearly tell you all the parameters, where it's going, how much XTZ you're spending, and then this shows this sort of applies it, it pre-applies it and lets you know what is likely to happen when it's applied. So now let's approve it. Okay, so now that exchange has been approved on the blockchain, the website isn't updating automatically, but we can wait for a minute for it to propagate into the Tezos nodes. And then if we reload this, we're going to see that the amount of TZG we have should go up about by 40. So right now it's 854. Let's reload. And it went up a bit. And so actually we should have took a look at the XTZ value. It went down. So now we can actually provide liquidity to an exchange. So right here I have XTZ, and it helps you calculate the equivalent amount because you have to provide an equivalent amount of XTZ and the FA1.2 token. So I'll do the same thing. So I'd be providing about 12 XTZ, 510 Tezos gold. And something isn't working. Let me try that again. Well, unfortunately on this screen there's a technical error. Let me try remove liquidity. So these are my my liquidity tokens from Tezos Gold. So this shows a proportion, basically a proportion of the entire collection of XTZ and FA1.2 that I own. So it's quite a large number, 4 billion, and the exchange has a little more than that, so I own most of the liquidity. But let's say I want to get rid of some of that. Let's say, like, what's that? 5 million. So that would return, if I get rid of 5 million pool tokens, that would give me 5.4 XTZ and 230 Tezos gold. Hold on. Okay, so I tested it. It should work. I'll approve it. So we're going to wait for it to propagate a bit. You can already see on the right-hand side that I've recorded the transactions. These are all recorded locally, not in a backend server, in the browser locally. That I requested to remove 5 million Tezos Gold pool tokens. So I'm going to reset this, or I'm going to reload this, and we should see this value change. So right now it's 12 million. We reloaded, and here you can see it went down by about 5 million. And proportionally, my XTZ and TZG should have gone up. So I think that should give you a basic idea of what Dexter does. So let's talk a little bit more about the details. Okay, so we went over liquidity. That's the two pools of tokens that exist in a single exchange. So each exchange represents, each exchange contract represents an FA1.2 token. So if there are multiple FA1.2 tokens, those each need an exchange contract originated. So users can provide liquidity, and they can burn a portion of their liquidity and get back equal amounts of XTZ and FA1.2. So we saw that in this screen where you can add liquidity. And then in this screen, we saw where you can remove liquidity and gain XTZ and FA1.2. So what else can you do? A user can sell XTZ to get FA1.2, and a user can also sell FA1.2 to get XTZ at the exchange rate that exists in the contracts. And you obviously can't buy more than exists in these contracts. And also to sort of help maintain the levels of the pool size of these contracts, large exchanges are sort of prevented by creating a slippage in the exchange rate. So if you do a very large trade, like you try to take 50% of the FA1.2 from the Dexter contract, you would get a much worse exchange rate than if you had tried to take 5%. So this is sort of to keep these things balanced and not have these exchanges emptied out and let multiple people interact with them. So this is sort of a review of the UI for the swapping for XTZ to an FA 1.2. And then in the same screen, if you click on the left side, you can drop down and choose another token, and you can decide to exchange it for XTZ. So that part is pretty clear. Now let's talk about the baking reward. So these tokens exist in this XTZ is going to sort of belong to the Dexter contract, and any contract can essentially set a baker who will essentially be sort of borrowing their staking power on Tezos, and they will be gaining rewards and returning those rewards to Dexter. So since this is a decentralized exchange, each individual may have their idea of who the best baker would be or who the baker they'd like. So each baker sort of has the power to decide how much of the rewards they're going to return and when they return those rewards. So there's nothing in the Tezos blockchain that says bakers must return those rewards. It's rather that they decide to do those, and because they have a record of returning those rewards, people are going to stake their XTZ with those bakers. So you could just set the delegate from the beginning when you originate the contract, but that's pretty inflexible because maybe that baker decides no longer to bake, so you'll lose out on those rewards, or they'll decide to keep them after some point. So we've sort of had a lot of discussion about a voting system versus an auction system. And at the beginning we thought a voting system where people who provide liquidity for these exchanges has the right to decide who the baker is of the exchange. But we sort of went over a lot of game theory issues, and we've come across a few vulnerabilities in that, one, people who are interested in a particular baker could provide a lot of liquidity for this, and they essentially own all of the voting power. Like if essentially they could have 51% of the voting power, they could give it to a particular baker and they can just keep those rewards and no one can say anything. So they get to keep all the money. Or you could have just a very split votes, like you have like maybe people voting for 10 different bakers, and so each baker is a very small percentage, so it's very easy for interested party to sort of take over that. Then where we're thinking about now is an auction system. So instead of saying that the liquidity providers can vote on who the baker is, the bakers come and they sort of give upfront rewards to bake for the exchange for a set period of time. So this way, the exchange is guaranteed to get some sort of rewards, as opposed to the voting system where someone can be voted in, they could steal the rewards, and maybe people would vote them out in the next round of votes, but there's also the risk of a large liquidity holder continuously voting for that particular baker, which presumably they may own and keep the rewards. So if you're interested in this issue with a voting system, there's a discussion on Tezos Agora that's pretty interesting that talks about all the pros and cons and ways it can be gamed. So right now we have the auction system, so bakers periodically bid for the right to be the Dexter Exchange's baker, and we don't really expect that they'll pay rewards. Instead, the bid compensates for the rewards that would go into this system. And so where are we now with Dexter? It's an open source repository. You can find it on GitLab, camelcase-dev Dexter. We're still working on a few things before we consider the first version of Dexter complete. So we're working on a formal specification and a formal proof. we would like to integrate Beacon into Dexter. So if you saw how I was using TezBridge, I had to switch back and forth between tabs. That doesn't really create a nice user experience. So one thing about Dexter is that we'd like to have a really nice user experience and let it be something that people who are not software developers can use and understand what's happening. We'd also like to optimize the gas costs of Dexter. Right now it's a bit high. We'd like to improve that. And finally, and once we have all that, we'd perform a security audit. And then these aren't done, but we're already thinking of version 2 and what we'd like beyond that. We'd want to support FA2, which is a much more interesting token standard and any other token standards that the community is going to be interested in. We'll explore other automatic market models. So right now we have a very simplistic one, but there's some things you can do with historical data. And if the system has a very trustworthy exchange rate, then it can even be used as a price oracle for third parties to use. Also explore alternative baking models. We'll get into a little bit later, but there are a few issues even with the auction system that can be abused. And then finally, create a reusable SDK. So right now, we have a set of code in ReasonML, so you can interact with Dexter on the front end. But if other people are interested in using this with other programming languages, other ecosystems, that's something we'd like to support. So I'd like to mention a few people because, yes, Camel Case has been working on this, but we've also been working in conjunction with other people. So first I'd like to mention Arvid. He's in the audience. You can wave to him. He's been working on the formal specification and doing a lot of conversation with us with gaming issues, problems he sees in the contracts, and it's nice to have a third party who's not involved in development sort of review the code. Also AirGap, they are working on Beacon, and that's going to be a very nice way essentially to have a wallet in Chrome and interact with dApps in websites. TQ Tezos has been working on the token standards, and they've helped us a lot with getting in touch with interested parties. We use LIGO, and we've also used Morley to develop these contracts, so thanks to those groups. And finally, Arthur Brightman has been involved also in discussing a lot of the game theory issues. So I want to open it up to questions now, and here, I won't force anyone to answer this question, but it's one sort of outstanding issue which basically states that in the auction system, bakers want to gain the right to bake for this exchange because it could have a lot of XTZ. People want to put XTZ into this because they not only want the transaction fees, they also want the rewards from baking. So there's a problem in that people could put in their XTZ, and once the rewards are rewarded from baking, they'll remove it, and then the amount of rewards it actually produces from a period of baking is reduced, and then these bakers are less incentivized to bake for these contracts, and then they won't bid for these anymore. So sort of an idea we have is to pay those rewards slowly, but we're still sort of thinking what the best way to do that is in actual code, because we're always concerned about reducing gas costs and making these as simple as possible to use. So any questions from the audience?
So my question is simple. So you have XTZ and Tezos Gold, for example.
Yes.
Do I have possibility to put on your contract Tezos Gold?
Do you mean to make, so each contract is paired with a particular FA 1.2. So Tezos Gold, you could have Tezos Silver.
So I can put Tezos token and I would have profit both from baking and from exchange.
Yes.
But if I put token,
Yeah.
I would have only profit for exchange.
Okay, so if you put liquidity, you have to have both. So you have to, and the amount you put has to match the exchange rate. So if you don't have any, you can buy some first and then put it on.
Okay. Other question. I put a lot of Tezos gold.
Yes.
And for some reason, all this Tezos gold is sold by this contract.
Yeah.
So how contract would be repay me if I want to withdraw?
Right. So now you're going to have a lot of XTZ. So you're going to be happy. Maybe if Tezos gold is so that would essentially mean that Tezos gold is now worth a lot of XTZ.
But how could contract calculate price if there would be no Tezos gold at all and no one supply liquidity?
So it sort of tries to avoid having, so you can't have one at 0 and the other at non-zero. Essentially, they at least each have to have one, unless there could be the case that the last liquidity provider removes everything and then it's 0-0. So now, okay, so I did mention the first liquidity provider decides the exchange rate. And then people can sort of, so it's an automatic market. The exchange rate is essentially a proportion of FA 1.2 to XTZ. So if I make this new contract, I put 1 XTZ, I put 1,000 Tezos gold. I've decided that 1 XTZ is worth 1,000 Tezos gold. So now for you to add liquidity, you have to abide by that exchange rate, but you can change it. You can change the exchange rate by either selling XTZ to the contract or selling gold to the contract.
So if someone want to use this smart contract to create new pair,
yeah,
it should have some Tezos and gold and should never remove this liquidity, otherwise something else would have control to control all the price.
I mean, if that matters to you, you can do that. So that can happen. It just depends if that, if that matters to you or not. If someone else gets control of the exchange rate, but it fluctuates depending on how much, like the size of these pools. So the outside world sort of has the ability to influence these by buying and selling, so they can sort of change the exchange rate. And we also sort of try to disincentivize large exchanges that empty one of the pools by lowering the exchange rate the larger the exchange becomes.
Okay. Thank you.
I have a document with the calculations for how all these works, and if anyone's interested, I'll point you towards that. But that'll just be in the repo. We have some documents that that explain what Dexter is and the various calculations.
Okay, any more questions? We have time. Okay, so if there are no more questions, let's thank James for his presentation.
Thank you.
So I guess we are ready for a coffee break. That's what is on the program. So we start again in something like 35 minutes from now. Okay? Thank you.
Parce que tu t'en fais ça va faire en quand même.
c'est à moi.
Oui, c'est pas mal que tu te branches toi. Alors, c'est pas dit que tu es le retour pour autant. Ce qui est important, c'est que vraiment, il faut que tu te remettes un peu comme ça et que tu regardes ce machin-là.
Ouais.
Donc, parce que tu auras un retour là-dessus.
Ok.
Voilà, donc ça c'est bon. Vas-y, montre. C'est quoi ce que tu vas nous montrer?
C'est ça.
Ce genre de choses, oui. Donc ça c'est bon. Ça c'est bon. Oui, donc ça c'est bon. En fait, c'est le.
Alors du coup.
Le truc, tu vois, le truc qui est un peu. Alors. Là, enfin, ce genre de truc, là si ça va, ça passe très bien en fait en vidéo. Donc sur YouTube ça va être top. Et puis ici ça va être un peu, tu vois.
Parce que sinon,
non, c'est très bien. Ce qui se passe, c'est que l'écran il est un peu illuminé là.
Et sinon, ouais, j'ai fait des vidéos.
Tu fais de la vidéo?
Ouais.
Trop cool.
Pour éviter justement.
Ouais, ça c'est parfait, vraiment. Ouais, c'est très bien. Et en plus, tu peux parler pendant que ta vidéo tourne.
Ouais, c'est le but.
Ouais, non, c'est
Est-ce qu'il y a moyen que je vois à quoi ça ressemble sur l'écran?
Faut demander au mec qui est là et il est pas là.
Ah.
Mais t'en fais pas, comme on a 45 minutes.
Non, mais parce que ça c'est pas du Full HD. Et des fois j'ai des problèmes quand je me connecte à un truc qui est Full HD.
D'accord. Mais là t'as pas. Ah oui, donc en fait ce qui se passe c'est que tu sais pas ce que ça donne.
C'est ça.
Parce que là t'es en. Il a vu qu'il y avait un autre écran.
Ouais.
Quand tu fais
normalement il s'est mis dessus, mais c'est pas sûr.
Et quand tu fais un render, il te dit quoi? Tu connais pas render?
Ah si, j'ai l'extender la musique, il est là, mais c'est.
C'est qui ça? C'est toi?
Ça c'est moi. Le DP1 c'est ça.
Ah, ça existe encore. D'accord.
On m'a donné ça quand je suis arrivé en stage.
C'est vrai? Tu vas avoir le contrat, non?
Dans longtemps.
J'ai cru comprendre ça.
Donc voilà.
On va faire une vérif.
Du coup, ça a l'air bien comme plan, genre des rappels.
Attends, remontre-moi le plan. Parfait, non, c'est juste très bien.
Comme ça, on dit ouais, c'est quoi une date finale, c'est ça. En vrai, il y a plus de trucs.
Ouais.
Tu sais, je suis très content d'avoir réussi à faire une blockchain. Donc smart contract sur Tezos. Je sais pas s'ils ont eu vraiment.
Si, bah, enfin,
je pense que ça fait jamais de mal de répéter.
Ah non, mais bien sûr, il n'y a pas de problème.
Les conventions.
Il y a un truc qu'il faut savoir, c'est que ta vidéo, à terme, les vidéos vont être découpées.
Et donc, de toute façon, il vaut mieux.
Et donc, il y a des gens qui vont regarder ta vidéo sans avoir vu ce qu'il y a avant. Donc, tu parles pour YouTube et pour la postérité et pas uniquement pour les gens qui sont là. D'accord. Donc, ça, c'est super important de prendre conscience de ça parce qu'il y a, d'une part, il y a 25 personnes qui suivent en direct.
33.
33 peut-être maintenant, je sais pas, il y en avait 50 ce matin, mais 49. Donc il y en a pas mal ce matin, là il y en a qui vont venir. Mais ça va être post-processé après, enfin, faut voir avec comment ce truc-là est payé, mais l'idée c'est de faire des chapitres. Et donc voilà.
Donc tant mieux.
Donc il y a deux choses importantes, c'est que ton truc soit un peu autocontenu, enfin pas trop compliqué, donc tu t'en fais pas, c'est parfait, et que tu parles bien là-dedans. Donc vraiment, il faut que tu t'y colles, ou alors que tu le mettes...
Coller, on va éviter du coup.
Non, mais que tu le prennes comme Guilux.
Mais là, il était comme ça, non?
T'as pas connu Guilux? Je sais pas si c'était bien.
Moi, je crois qu'on entendait bien, non?
Ah bah ici, nous, oui, mais encore une fois, ici, on s'en fout. Tout le monde va t'entendre. Même si tu parles à côté. Alors que, toi, la question, c'était vraiment YouTube. Donc là, c'est YouTube, ils sont dedans. Là.
Ok, ouais, ça marche.
Et donc ça veut dire qu'il faut éventuellement que tu modifies ça. Enfin, tu vois, on te fait mettre comme ça parce que la caméra qui te prend, c'est celle-là.
Comme ça tu regardes.
Donc celle-là, en fait, tu as vu tout à l'heure, ils font une petite vignette sur le côté, et puis il y a tout ça à la côté. Donc tu parles à la caméra, enfin la foule est là, le micro est là, et puis voilà.
Ok. Et attends, du coup, juste, je fais une validation encore. Je finis, genre Michelson un petit exemple. Hugo un petit exemple. Et alors on est moderne ici.
J'ai jamais réussi à utiliser ça. Je trouvais ça marrant une fois.
Et final après les clients, comment utiliser le Tezos Client.
C'était un peu l'apothéose de la journée. Hein. Après, il y a Truffle.
Non, c'est ça l'apothéose. Et après.
Ton exposé.
Ouais, lâche. C'est bien, ça va pas la pression.
Non, c'est montrer la valeur.
La spec.
Oui, non, excuse-moi.
Merci. Je me suis dit que c'était l'intention. Ça marche.
parce que là, il faut quand même qu'on regarde.
Ouais, ce serait.
C'est quoi comme application qui fait tourner ton machin?
Ça s'appelle Firefox.
D'accord, donc c'est du JavaScript.
C'est ça.
Ok.
Est-ce que c'est branché? Mais ça, non, ça devrait aller parce que en fait j'ai découvert tout à l'heure en révisant, parce que je l'ai branché sur le vidéoprojecteur chez moi. Il a perdu sa batterie en fait quand il y a un câble HDMI quand il boot. J'ai pas ces problèmes là que j'ai quand j'ai pas mis le câble HDMI en bootant.
Oui, donc ça j'ai. Alors, faut faire gaffe. Faut pas trop jouer avec ça. Ce câble est fragile, en fait, on l'a collé tout à l'heure parce que.
Hello.
Bon, voilà.
Ok. Ah, ça va faire trop bizarre de parler dans un micro. Il y a du feedback. C'est ça qu'il faut.
Non, mais c'est vrai.
Non, j'aimerais beaucoup faire des cours. Parce que, genre, vraiment, tu sais, avec les mêmes gens, tu t'habitues, tu vois progresser, tu vois un peu.
Mais il y a, toi, là où ça aide, c'est. Alors, je comprends, il y a des gens qui n'ont pas de problème, des gens qui ont le problème de parler à une salle, pas de parler. On a vu tout à l'heure passer par exemple, Dany et Christian. Christian, on sentait qu'il avait de l'expérience.
Ouais, j'ai vu sur YouTube.
Dany avait plus de mal à poser son ligne. Les cours, si tu fais pas ça, tu survis pas. Les élèves, ils te tuent.
Oui, c'est ça. Mais la différence, c'est que moi, j'ai complexe d'infériorité. Alors qu'en cours, je sais que je sais qu'ils savent rien. Mais alors que là, c'est pas. Je me sens plus exposé.
Il y a un truc qu'il faut. Enfin, le truc qu'il faut se mettre, c'est pas une question. Enfin, il faut vaincre les sentiments d'infériorité, mais pas remplacer par un sentiment de supériorité non plus. Le truc idéal et qui est réel, enfin, c'est la vérité vraie, c'est que ce que tu dis a une valeur. Et tu apportes quelque chose à la salle. Que ce soit une salle d'étudiants, une salle de gens. Et le fait que tu parles aussi un truc qui est enregistré, toi, tu apportes des choses aux gens qui t'écoutent. Les gens, ils ont un certain respect. Alors, il faut pas. Voilà, les élèves dans une salle, ils peuvent ne pas avoir le respect immédiat pour.
Ouais, mais tu fais bien, absolument.
Mais si tu sais que tu apportes quelque chose, forcément les gens le voient et respectent ça. C'est ça qu'il faut garder présent à l'esprit, c'est que ce que tu dis vaut quelque chose.
Ok.
Ça marche.
Et du coup, ouais, ça détend, tu fais.
Pas de pression, hein, c'est.
Ouais, c'est vrai, parce que genre, j'aime beaucoup ce genre d'exercice, mais ça me terrifie à chaque fois. J'ai envie de faire ce genre d'exercice, mais ça me terrifie à chaque fois.
Non, mais je comprends, mais donc tu vas voir, tu vas être content de ça, c'est sûr, à la fois parce que c'est fini, mais aussi parce que tu as réussi. Il y a une vraie satisfaction à se dépasser un peu. Ouais.
Et tout à fait.
Moi, mon dernier déplacement, c'était, je suis allé aux États-Unis à peu près une semaine de vacances avec ma femme, et j'avais cette espèce d'angoisse. Je crois que tu as vu déjà.
Je fais que le Québec.
Les feux rouges sont au milieu du les feux rouges sont au milieu des carrefours. Et moi, depuis que je suis tout petit, je me dis, jamais j'arriverai à m'arrêter là où il faut. Et c'est complètement stupide, ça. Et j'avais donc même longtemps après avoir été tout petit, j'avais encore cette espèce d'angoisse qui était restée. Donc, oui, mais ça, je l'ai écrangé, j'avais très peur. Et en fait, j'étais super content de m'être dépassé. Voilà, donc à chaque.
J'imagine. Mais ça a aidé parce qu'on s'approche quand même d'une présentation qui va être reprise. Parce que là, je vais pas te faire de nouvelles présentations qui sont jamais vraiment la même chose. Donc, j'arrive pas à prendre un footing non plus.
Celle-là va être reprise, mais il y en aura d'autres.
Ouais, justement, c'est genre, on passe encore plus de familiarité avec le matériel présenté. Donc,
non, bien sûr. Et encore une fois, les gens, ils écoutent, déjà, s'ils savent déjà,
ils sont bons.
Ils n'écoutent pas, je pense que les gens qui écoutent, c'est qu'ils ont le tri également à ce que tu veux.
Et non, le truc qu'il faut un peu faire, c'est l'anglais, tu vois.
Alors ça, c'est pas facile, donc il faut, voilà, bon,
qu'il y aurait moyen que je teste, voir si ça passe bien sur l'écran?
Les slides?
Ouais.
Allez-y. Ouais, c'est bon, les slides. Ouais, ça passe.
Du coup, ça... Ouais, ça passe comme ça. C'est relou, ça.
Pourquoi?
Parce qu'idéalement, ce serait en full screen. Par exemple, là, il y a les... En gros, là, il y a les slides, et là, il y a... Ouais. C'est pour ça. Je pensais que ça allait faire ça.
Ouais, moi, c'est la recopie de l'écran, quoi.
Ouais, c'est ça, mais j'ai un problème des fois avec les écrans qui sont plus grands que la répartition de mon ordi.
Voilà, non, ça doit fitter. C'est bon, ça fit ou il faut...
Du coup, j'ai tenté un nouveau truc pour essayer de le faire bien, si ça vous va.
Eh ben, allez-y, comme ça affiche, on est bon.
C'est quoi la résolution que vous utilisez pour faire une copie de l'écran?
1080 basique, je crois.
Ok.
Après, le vidéoprojecteur, il n'est pas incroyable parce que du coup, on sort en HDMI et après, du coup, c'est un convertisseur qui se met en VGA, du coup, la qualité n'est pas incroyable.
C'est vraiment. Là, il y a du texte qui s'affiche. On voit les bouts de texte.
En bas, là?
Ouais. Mais c'est pas votre faute. Hein. Enfin, c'est le
format de l'image, la slide, je crois, qui est comme
ouais.
ça.
On va faire avec. Ça, c'est exactement le problème dont je te parlais. C'est que il prend.
Ah oui, c'est que pour toi, comme si tu avais un écran virtuel.
Et du coup, moi, il me l'affiche en plein écran. Mais,
parce que tu as demandé un miroir.
Oui, et il veut pas mettre celui-là en principal. Je sais pas.
Pouf. Résolution. Donc toi, tu peux pas monter ta résolution et tu peux pas changer la sienne.
Si, mais après, non. Et après, ça devient encore plus moche.
Est-ce que tu veux que je te passe mon ordi?
Je pense qu'on n'a pas le temps.
On a un quart d'heure.
Ouais, mais parce qu'il faut du soft spécial pour le lancer. C'est un serveur web et tout ça. Parce que sinon, ce que je peux faire, c'est ça, essayer de suivre ce qui est ici.
Oui, sinon tu... Ah oui, ça c'est pas mal. Et tu vas mettre en plein écran là-dessus?
Ça ressemble à un écran là.
Parce que ça va présenter l'avantage. Alors le problème, c'est que c'est pas super confortable pour toi, peut-être.
Ouais. Mais
tu mérites vraiment un autre ordinateur. C'est dommage.
ah, c'est vrai, j'attendais aussi qu'il fasse des écrans en 3,5. Parce que c'est plus pratique pour écrire du code. Mais en fait, le seul qui fait ça, c'est Huawei. Et il est plus disponible nulle part à part à 3500 balles au lieu de 1500.
Il arrive à passer en mode
sans doute, je pense.
Bon, écoute, là comme ça, c'est pas mal. Effectivement, toi, t'as pas de retour, enfin, ton retour n'est pas évident.
C'est mieux que rien.
Avec une zapette, ça t'aide ou non? Tu veux un clavier?
Le truc, c'est que j'utilise ma souris pour dire par là.
Ah oui, d'accord.
Je fais comme ça. Là, ici. Là, je vais pas le faire comme ça. Si on avait une tablette graphique, par contre, je ferais comme ça, je pense.
J'ai deux ordinateurs. Le mien perso, il y a un écran. Tu peux toucher.
Ah, écran. Ah oui.
Un touchscreen, quoi.
Ok. Ah oui, ça aussi, c'est cool.
Écoute, voilà, tu fais deux autres. Bon, écoute, comme ça, c'est bien.
Moi, je me dis c'est le mieux.
Après, évidemment, c'est pas super confortable.
Ouais.
Pour être sûr que les gens de Tezos sont deux webcams.
je trouvais que c'était bien. Hein. Ils ont fait tout le résultat. Après, il n'y a pas beaucoup d'animaux qui sont autant dans notre identité que le chameau et le poulpe. C'est vrai.
On va être prêt pour 4 heures pile. C'est bon? Tu me dis... Enfin non, je peux commencer à 4 heures. Tu me dis quand c'est bon ou je te dis on y va. Pardon? Je peux y aller maintenant? On va attendre 1 minute que les... Ah oui, ok. On va attendre 4 heures pétantes.
Oui, je sais même pas sur quel slide je suis là.
Ah oui, mais il va te mettre le truc dès que je dis on y va. On va attendre 4 heures. 4 heures et quelques secondes.
Du coup, ça fait... Ah, je plein de trucs.
Tu veux quoi, un timer? N'en fais pas, je m'en occupe.
Je fais à peu près une demi-heure. Il me semble.
Tu as 45 minutes.
Ouais, avec les questions.
Donc tu es très très large. Ouais, je t'attends pas trop à les questions. Prends ton temps.
Pas de soucis.
Tu as 45 minutes parce que j'espère que les autres vont être là au niveau. Voilà. Donc là, tu as ton retour transparent. Ok, Benjamin, on est prêt. C'est bon? Ok. So welcome back to the Tezos Developers Day in Paris 2020. This is the last session of the afternoon, of the day. And that session has 2 talks. The first one is by Alexandre Dussault from Nomadic Labs, who will explain us how to build a simple decentralized application. Up to you.
Yeah, perfect.
In the microphone.
So yeah, I'm a developer from Nomadic, and going to talk to you about decentralized applications. So the way I intend to do that is in 3 parts. Firstly, give you a brief reminder about how the blockchain works, how smart contracts on Tezos works. Then I will try to give you an overview of what tools are available on the Tezos ecosystem, and then give you a small example. So when we say decentralized application, really what we mean is a client-facing application that calls from some state on the blockchain. But in reality, it's a bit more complicated than that. Because when we say on the blockchain, it's actually a smart contract that is located in one of the blocks. So how can the application talk to the blockchain? So it goes through what we call a node that has a local copy of the blockchain. And this node exposes an RPC interface. Think of it like a RESTful interface. It's a small function that you can call to query something like the head of the blockchain, which protocol version you are in, or to call a contract. But it's a bit rough to call that, so we have some wrappers around the API, which we call a client. So for example, if you just use RPC from the node, you need to do 4 different ones if you want to call a contract. So this is a client, and the client is made of 2 parts. Something that deals with the RPCs, and something that signs the transaction, because we are on the blockchain, so everything needs to be signed. And basically, the application will call a client that will call a node that will do some operations on the blockchain. So a smart contract on Tezos is made of three main parts. First, the balance, which represents the number of tokens that are stored on the contract. Some storage space, which is persistent space that remains between contract calls, and the code of the contract, which is itself divided in three. Firstly, some code that describes the different entry points that you can call, something that describes the shape of the contract, which could be a number of a more complicated object, and then the code instructions. So in Tezos, there is conventions to respect. Basically, a contract, any contract must take as its input a pair of the parameter that is given by the user when he calls a contract, and the current value that is stored in the storage. Then the contract will execute and execute all its code, and when it has stopped doing that, it will output the transaction to emit and the new storage value. Because on Tezos, a contract cannot do side effects. So if contracts want to call another contract, it will need to emit a transaction as its output. So here is an example of a contract call. If you have a wallet contract, which basically holds some tokens for you and allows you to do transfer, and let's say that Alice calls that contract with the entry point send, which is basically send Bob 200 meters. You can see that it will call the contract, and the contract, when it has finished executing, will transfer 200 meters to Bob. One thing to note here, if the contract didn't have enough funds to transfer 200 meters to Bob, that transaction would not happen, and that one would be rolled back, and Alice would get back her money. So now I'm going to talk about the smart contract languages that are available on the Tezos blockchain. And the first of them is Michelson. It's basically the assembly of the Tezos blockchain. Its aim is to be something kind of like the Ethereum bytecode, and to be a low-level language that other languages compile down to. However, it also tries to be somewhat readable with some efforts. It's also statically typed, which is nice, and is tag-based, which could be esoteric to some of you. Here is an example of a simple counter in Michelson. A counter contract basically only do one thing. It has one entry point, and every time you call it, it increments its storage value by 1. So I won't go into too much detail, but basically you can see here that it doesn't take any parameter, that its storage is just a natural number, and its code, it says take the storage, add 1 to it, and then respect the convention call. Then you've got LIGO, that is a high-level language which has variables, supports arithmetic with binary operators, which is nice, and also supports several syntaxes, like inspired by Pascal, OCaml, or ReasonML. There's also a web IDE, which is always nice. Here is the counter LIGO, so that piece of code is almost the same. And then you can see that we respect the convention call by taking a parameter or storage tuple and then incrementing it by 1. You've also got SmartPy, which is a Python library for creating smart contracts. It's basically a meta language built on top of Python and has a very Python-y feel. One of the nice features about it is that you can do tests and deploy directly into the online editor. So here is our counter with SmartPy. In the init, we can see that we set the storage of the contract to 0, and then the only entry point, we increment it by 1. So I'm now going to talk about clients, which are, like I said, wrappers for RPCs. There's many of them available to you. There's Tezos client, which is a command line client, Taquito and Consei.js, that are JavaScript one, and Consei.py and PyTezos, which are made for the Python world. So Tezos client is one of the first clients for Tezos. It's in command line, and it was made in Nomadic. So to do a simple transfer, you can do following syntax. It's basically you call transfer, then the amount, and then the sender and the receiver. So if you try to run that command, Bob will send 3 tests to Alice. But you can also originate contracts by calling originate contract, then the alias in which you want to name your contract, running the code, the Michelson code of your contract, and then the initial storage value. Because every time you want to originate a contract on the Tezos blockchain, you have to specify an initial storage value. And then you can call that contract by doing a transfer, because every contract call is basically a transfer. So Eve tries to call the contract vote that we originated here with the entry point vote and the argument Detroit. Then there's Taquito, because while Tezos client is nice, you can't really build an application with it. So here comes Taquito, which is a TypeScript library, which means you can use it in your web app. And it's pretty nice because you have smart contract abstractions. You've got abstraction over the RPCs with type checking, which is always nice. You can inject transactions on the chain. You can use different. You can talk to different nodes and use different signers. And lastly, you can write some code in ReasonML, which I like personally. So to configure it, you can call set provider, and you can specify a signer, a forger, a config, which protocol you would want to run and which node to call for doing RPCs. By default, there's no signer configured, so you can only query storage, and you cannot do transactions. And the protocol is fetched by an RPC call to the node. So if you want to query the storage of a contract, you can do that in the following way. You have to call tezos.contract.at and then the address of your contract on the chain, and it will give you back a promise, because it's asynchronous, because you have to do like a network interaction. And then you can, based on that contract object, you can then call the storage method. So let's say you have a contract whose type is like this, which is a record having candidates, a map which maps a candidate name to its number of votes, and a timeout which specifies when the vote ends, and you try to call contract.storage on a contract of this type. You will get the following JavaScript object. So let's say you want to call the contract now, and let's say it has 2 entry points. First one is vote, for voting for a candidate. And the second one is to create a new vote when the old one has ended. Basically, Taquito will parse the code of the contract and know which entry points are available to you. You can access them through the methods, method on the contract object, and then you can call each entry point, like vote or new vote. And then there's TestBridge, which you've heard about in the last presentation. It's basically a way to link Tezos and decentralized applications. It backs a local signer and something akin to MetaMask in Ethereum. Taquito can use TestBridge as its signer, and one of the nice feature is that you can use TestBridge to connect to a ledger, for example. So now into the example, I'm going to show you a single project, a crowdfunding app. So smart contract language I've decided to use is Ligo. The application will be a simple JavaScript front-end. And so we will use Taquito to call to a node. The signer will be TestBridge, which will be used with Taquito. And the node will try to use this sandbox node. So a sandbox node is like having a local blockchain on your computer. What's good about that? It's really for ease of development, because you can have fast baking. Because, for example, on the mainnet network, there's something like a block every minute, which is a lot of time to see something happening. And you can say that you want to bake every 5 seconds, for example. Another nice things about that is that when you create a sandbox, by default, there are 5 accounts which are already on the chain, and they have like 4 billion Tez. So you can use that to try lots of things. So to launch Sandbox, you can use a tool called Test Tool in the following way. So you say you want to create a sandbox, then you specify the network, in this case Babylon Net. Then which account do you want to be the one to bake? Then the interval of time at which that baker will bake, and then the port at which you want the node to expose the RPCs. And then we want to configure Taquito to talk to that node. So we try to put localhost and the port we specified and use TestBridge as our signer. So the idea, for those who don't know what crowdfunding is the practice of funding a project or venture by raising small amounts of money from a large number of people, typically via the internet. So we'll try to specify that a bit more in detail. So a project creator creates a project, specifying an amount of tokens to attain and a time frame in which to raise that amount. This is done one time, so it feels like it could be done at origination, when we originate the contract. As long as time has not run out, anyone can now pledge a certain amount of tokens to fund the project. This could be one of our entry points. When time has run out, there's 2 ways to proceed. If the goal was attained, the project creator can transfer all the tokens on the contract to their account. Which means if I'm a project creator and I say like, I want 100 Tez to develop my project, and if people have given like 200 Tez on this contract, I can get back to 200 Tez and try developing what I wanted to do in the first place. So this could be a second entry point. And lastly, if the goal was not met, each individual person that donated some amount of tokens to the contract can now get back what they gave. So this could be our third entry point. So following what we said, we can see the type of parameter, which is pledge for the pledge entry point, fund for if the goal was met, and claim back for if it wasn't. You can see here that every entry point takes units because everything we need to do what we need is actually inside the transfer. For example, the amount of money that was transferred, or who sent the transaction. The storage of a contract would look a bit like this: a string to describe the project, a goal to attain, which is a natural number, a map of pledges, which is basically to say who donated what. This is useful for the claim back. And lastly, a timeout to specify at when point the donation is over. So to originate the contract, we've decided to use Tezos client. But since it's a bit of a longish command to write, we've decided to use a makefile, which is basically a way to write some shell command easier. So we've got two targets here. We've got the compile one, which basically calls LIGO and compile contract to transform the LIGO contract into a Michelson one. And then the originate, which will do the origination, basically create a new contract called crowdfunding, running what we just compiled, with an initial storage that is specified here. So some people that will develop contract in LIGO are not necessarily familiar with Michelson. So LIGO proposes a method called compile expression that will transform a LIGO expression into a Michelson one to originate the contract. So this is the web page we kind of want to have, basically saying the goal, how many was donated, when the contract ends, and the way to specify an amount of money to pledge. So in HTML, that looks a bit like this. What's interesting is we've got button called button pledge for pledging, button fund for funding, and button claim for claimbacks. So now in the JavaScript code of our application, we want that when the user will click the button to pledge, for example, or to claim back, the Tacto will call the contract on its correct entry point. So for example, here, we try to find the button claim, and we add an event listener, which basically says, whenever the user clicks on this, we will call this method called callContract with claim, which will do methods.claim, which is what we explained before. So basically, what this amounts to, what happens really when the users click on a button. So the user clicks on the button pledge, the app will then call Tacto, that will in turn call the signer. At this point, the user needs to input its key in a test bridge to really sign the transaction that will be given back to Tacto. Tacto at this point will return a promise to the application that will be fulfilled when the operation is really included in the blockchain. So then it will inject into the node that operation and pull the head to see if the transaction has been included. And when it has been done, it will resolve the promise and the app will update its UI. So now a bit of demo. I've tried to record some stuff for avoiding the demo effect of things not working. So here is the origination. And we can see that our contract has been originated at this address, which is KT1 something. So if we try to pledge on that contract, which wants 300,000 meters, and we don't have anything on it. If we try to pledge, it will open test bridge, and you can see here that that we are on Babylon Net, and we are indeed querying the local node. I'll try to give money with Bootstrap 1. Then we can see that our request did come from our app into our local node. Then we prove. We see that it's okay, and when we get back to the page, the result has been updated. Now for funding. So we can see that Bootstrap 1 has an amount, a balance that ends with a 2. And Bootstrap 1 did originate this contract as a creator and wanted 300,000 meters. And somebody donated a whole Tez. So the goal was met, and now we can fund this project with the Tez. So we'll click fund. Input is very secure password. And then approve the transaction. And now if we try to access its balance, we can see that it gained the Tez minus the transaction fees. And lastly, the claim back. So if we have a contract like this, where 2 people have donated money, for example, this is Bootstrap 1, and he gave 20 Tez, and this is Bootstrap 2, and he gave 30 Tez. But the project creator, which is Bootstrap 1, wanted 100 Tez. So the goal was not met. So people will now be able to claim back their money. So like always, choose Bootstrap 1 account, use it as signer, approve the transaction. See, there's less money right now in the contract. And if we try to fetch the balance for Bootstrap 1, we can see that 20 Tez have been added to his account. All right, that finishes my presentations. If you have any questions, shoot them. And always remember that we have a Stack Exchange in which we try to answer any question. Thank you.
Okay, thank you. So we have a lot of time for questions. So we need questions because we have too much time because the next speaker is not online yet. So anyone willing to ask a question about how to build a simple or not application? Yes, good.
Overall, what was your experience developing the contracts? Did you have a lot of trouble, or how do you feel about the ecosystem?
Like when I started, SmartPy and LIGO were not really developed yet. But it's getting really good now because LIGO has really made its documentation better, and it's quite easy to use right now. There's lots of. I really liked SmartPy's IDE as well. I think it's really, and like you said, there's a beacon on the way, and I think that this will be a lot easier to use than TestBridge for about UI and UX. Yeah.
Okay. Thank you.
We had one more question here.
My question is about TestBridge. Can you customize look and feel?
Sorry?
Can you customize the look and feel?
I don't think so.
No.
No. Alas.
Thank you.
What would you want to, if you had to do it again now, what would you want, what would you need to this being easier now? I don't know, tool, methods, information. You mentioned documentation earlier. What is still missing?
And what aspects?
Any of it. Either would you use a SmartPy for? I mean, for what? If you had to do it from scratch today, what do you think you would need that you missed last time?
Like always, like I use VS Code, and having lots of extensions backed by language servers and stuff like that is, I think, really key to getting people to write more and more things.
Thank you.
Okay.
LIGO needs a test framework.
There's one that's kind of development, PyTest LIGO, that you can use. I'm not sure about. It's on Abate repo, I think. Okay. So yeah.
Okay. One more question. Okay. Let me.
So also in regards to testing, so when you mentioned the lack of unit test framework for LIGO, so that's only unit testing. But I guess that when you want to do more system type testing, then you have a lot of clicking around in the browser to do, which sounds like it will be very boring in the long run. So I guess this is not actually a question, this is a statement. It would be nice to have something to do all of that automatically and do kind of full system testing.
Yeah, definitely.
Do you agree?
Yeah, I agree.
Okay, do we have any more questions? Nope. Thanks again, Alexandre. So our next speaker is now online. Benjamin, can you have it on the on Zoom? So the next presentation will be about the deeper and deeper relationship between Truffle and Tezos. The speaker will be Nicolas D'Andrea. I hope I don't. I hope the name I have for you is correct. You are head of engineering at Truffle. Can you hear us? Okay. Can you hear us?
Yes, I can.
Oh, good. Okay, excellent. I'm sorry. Okay, so it's you have plenty of time. The initial presentation was 15 minutes, but you have more time if you need. So take the time that you need. Thank you, Nicolas.
Sure thing. Yep. Is this live?
Excuse me?
Is this live already?
Yes. So if you share your slide, the windows on which you have your slide, that would be great. Yep. Perfect.
Yeah. Has it been working to do this?
Yeah, you have to go full screen.
There we go.
Yeah, that's just perfect.
Great. Well, hello, everyone. Thanks for sticking it out for the rest of the day. Last talk. Sorry we couldn't be here in person. I'm filling in for Cruz Molina, our engineer who's worked on the Tezos integration, if you're familiar with it. I'm Nick D'Andrea. I lead engineering for Truffle Blockchain Group. So for those of you who aren't familiar, Truffle's a development tool around the smart contract development experience. So that means compiling your smart contracts, providing a mechanism for you to write and run automated tests, run deployments. If you were at Matej's demo, he probably gave you the idea. So Truffle started on Ethereum and Ethereum-like chains, and Tezos has been this an excellent stepping ground to expanding that. And so I'm proud to announce that we're releasing our initial version of Truffle with Tezos support, which I guess you've all already seen. So I wanted to go over some of the features that we've covered. I wasn't going to do another demo, especially because Matej's was so much more comprehensive than mine would have been. But instead, I thought to, I guess, just talk about, well, what does this release include? What is our initial Tezos support? What does it look like? What's included? And to start, well, that's LIGO support. You saw that in the demo today. And what this entails is not only will Truffle talk to the LIGO compiler and pass the files and handle the output, but Truffle also downloads the LIGO compiler, provided you have Docker installed. Truffle has a mechanism for automatically downloading the compiler, because one of the things that we want to provide with Truffle is a user experience that doesn't have a lot of fuss. So we go to Docker Hub, we do the Docker pull for you and get the version, the correct version, hopefully. and get it all set up so there's no configuration on the user on your part, like as a smart contract developer. And so you can just define a Lego file and then run truffle compile, and it'll persist the output for you. Then from there, of course, you might want to deploy to a local sandbox. You might want to deploy to a public test net or mainnet. And so Truffle Migrate provides that. You can configure multiple Tezos networks to connect to, and you take those Lego contracts that you wrote and compiled, and they'll get deployed to whatever network you choose. And of course, we have to test that our contracts are correct. This is way less exciting a test than Matej had on screen a couple hours ago, but hopefully it gives you the idea if you missed that presentation. This is just kind of taken from the example box, the official Truffle example box, which I think Matej has trumped. But then, of course, you have to interact with your contracts. And so we provide our contract abstraction, which takes the low-level details along with your source and metadata information. And this is thanks to Taquito's help for doing the auto detection and the network communication. But Truffle has a feature where it will detect a contract's interface, like the publicly defined interface for a contract. In this case, that counter has an increment and a decrement. And Truffle's contract abstraction will generate JavaScript methods. And importantly, those JavaScript methods will also take JavaScript data types. And the idea is that this contract abstraction is responsible for encoding those data types, in Tezos' case, into native Michelson in native Michelson calls, and then emitting the node RPC requests and handling the lifecycle of the response and all of that. And so we are releasing these features as kind of an initial version. We've tested it. And we hope that this is kind of a good groundwork that we're laying for this integration. I'm really excited about it. Everyone at Truffle is very excited about the direction that this has gone. I guess this is probably all. You've already seen these examples or similar ones on screen. So I wanted to also talk about, I guess, some of the key ideas, maybe to paint a bigger picture about what Truffle's going for. And thinking about it, I broke it out into these, and I guess to go over them, it's Truffle a goal of Truffle's is to create interfaces and workflows that match the high-level language, so that, because that's what smart contract developers are writing, right? You write your entry points and you define in Lego the algebraic data types that, like type action, that example that's on Lego's page, like. Those are the terms that Truffle wants to allow the user to work with, rather than Michelson's pair, nested trees. So that's kind of at the core of it. And Truffle should hide the details by default, but allow access to them. Of course, people need to write Michelson and will continue to need to write Michelson and read Michelson. And so Truffle should also provide access to that, but kind of when you ask for it. And then all of the information that Truffle keeps should be persisted. And this serves two purposes. One, for example, you don't have to recompile your contracts when you migrate. If you did a Truffle compile and you immediately followed it with the Truffle migrate, having persistent information on disk, Truffle just looks it up and says, oh, okay, I don't need to recompile. But it also gives us a place to track all the metadata about the contract, so that, we have the source information from Lego, so we can feed that to Taquito, which can tell us, oh, these are, this type action is broken out into these entry points, and they match up with the Michelson entry points. I hope I'm not getting too technical, but I'm guessing this is a technical bunch. But beyond that, there's this goal of flexibility, right? Truffle downloads the compiler for you automatically for the languages that we support, but we also provide a mechanism so that you can configure which specific version you want. And so it's like optional default, like optional configuration. You don't need to configure anything, but of course use cases do vary. And so Truffle's an opinionated framework, but we want to give outs, right? You don't always want to be subject to those opinions. And so that's kind of one of the key ideas. Like, well, we'll offer the opinion by default. And we hope it's, we think this is a viable way of doing things, but, please plug in something different. And then beyond all of this, especially moving into this work we've been doing with Tezos, we want to provide this same user experience, right? We have this history of supporting Ethereum, and the Ethereum community has been very supportive and provided a lot of feedback over the past 4 or 5 years of the project and refined it for Ethereum's use cases. But on Tezos, it's a different architecture, different languages. And so the kind of the direction that we see Truffle going is to provide that all of these key ideas, right? Like sensible defaults, high-level abstractions, but do it in a way where it's the same experience no matter what blockchain you're on, so there's no cognitive dissonance, if that makes sense. So anyway, the Truffle Tezos integration is a lot of glue code, really. Like we interface with the LEGO compiler, and Gabriel from LEGO has been enormously helpful in getting that set up. That was one of the first things we did. And then Jay and Simone on Taquito, Matege's work. Matej got the sandbox, Flex Tesla sandbox working by default in his Truffle box, and we took it for the default Truffle example box that we give you. And that's so much better than waiting at the time for Babylon Net, to mine or to bake, excuse me. And of course, to Tocqueville Group, TQ, and the Tezos Foundation for the support the financial support that has enabled this. This is a project that we've been very excited about, and being able to make it happen has just been an absolutely incredible experience. And to the Tezos community at large, you are an incredible community. Your early feedback on our releases, the Alpha Tez series, it's just been incredible. It's been enormously helpful in helping us to guide this support and this integration. So thank you all very much. Anyway, here are instructions if you want to install Truffle. One more, there we go. I'll leave this on screen. If anyone has any questions, please. I got at least 4 minutes, possibly more. Well, I guess this was supposed to start.
Questions? No. Oh, yes, one.
Let's ask. Okay. So one of your key ideas was to have a similar user experience on different blockchains, which is a good thing. So there are some things which are very different on Ethereum and Tezos, notably how you call other contracts. So in Ethereum, you can call other contracts during contract execution, whereas on Tezos, you have to do it in continuation passing style. So these two things are quite different. So my question is, do you have some kind of abstractions in mind which would kind of unite these two approaches? Is that even something that you would wish to do? And secondly, a more open question, do you think it might be possible to use the Truffle suite to reuse work that has been done for Ethereum? So reuse smart contracts and dApps and deploy them on Tezos.
So I'll answer that one first. There was a project to convert Solidity to Michelson or to LEGO, one of those a couple months ago. If there was any progress made on that, then it could be viable to take whatever the source language is there and expect some kind of interoperability, although I don't imagine it would be totally seamless, but viable certainly, or potentially viable. And then you bring up a good point about the continuation passing style, and I must admit that's not a specific distinction that we've looked at mostly because we're kind of fortunate that Truffle's abstractions don't extend that far. Like we don't, like the Truffle contract abstraction is just the operation, not the individual transactions. So I don't think we have to worry about that. I mean, there's analysis tooling that's been built on top of Truffle for Ethereum that just wouldn't work. You know, any tooling that does go that deep and look at the internal transactions, you know, the calls that contracts are making to each other. That seems like something to keep in mind, though, because I could see, for instance, I mean, Truffle has a lot of features. Truffle has a solidity debugger. If we wanted a LEGO debugger, we would have to handle the vastly different way that Michelson works in that case. Does that answer your question?
Yes, it does. And I also think that maybe it's a good thing that your abstraction does not extend so far, because maybe the programmer should be aware of the fact that inter-contract calls are not the same in Tezos and Ethereum.
Yeah.
Maybe. I'm not sure, but...
Well, you scared me for a second there with that question. I'm like, oh, wow,
that's
significant.
Not trap you or something. Just,
no, it's a big distinction, right? Yeah, but people use Truffle for things that would expect things to work a certain way. So it seems like this is a question that will be asked again in the future for, you know, some specific reason.
Okay, one more question? Yes.
This is sort of piggybacking on that question. And so from what I understand in Ethereum, you have events in the contract, but you don't have those in Tezos, though I can imagine there's a way to sort of recreate that. Is that something that's supported in Truffle or something you would be concerned about?
That is not currently supported because there's just no equivalent in Michelson. To be honest, there's, I guess, 3 or 4, right? And I don't know the most current status, like with Carthage, but my list has been views, like read-only methods, contract constructors, and that's a language constraint, not a Michelson constraint. And then events, logs. And it seems like views are starting to be more well understood. Constructors, I think, are solvable entirely just as a language concern. And then events, I don't think until there is a solution for some kind of logging, I don't see a way to implement that for Tezos in Truffle. But you guys make a lot of protocol upgrades, so I would not be surprised if it's forthcoming.
I mean, I think you could sort of recreate it off-chain. So you could use an indexer and sort of evaluate the operations that are occurring. Whether or not you want to do that, I don't know. But that would be how it would work in my mind without some sort of protocol change.
Yeah.
Just something.
I like that. Yeah, I like that kind of solution. Like, I was thinking about that. Something I've noticed in the difference just in the community mindsets is that Truffle's gotten away with having expensive gas costs for things like storing migrations on chain all this time. And all the Tezos developers that we talked to were like, why are you doing that? That's not how we do things here. And so it's like, it's opened my mind a little bit to like, okay, maybe constructors can just be a totally different mechanism or views could be entirely off chain, but just a compiler feature. I don't know. So yeah, you could do it with events and have a storage. Yeah. I think if there's something viable there, that maybe by that point when there's a best practice, then that could be added to Truffle, maybe as a configurable way if it's not a standard. Yeah, definitely something to think about. Thanks for mentioning that.
Yeah, thank you.
For events, it's kinda, I have one proposal because we have same problem. We have no complete solution right now, but one of mode of transpiler which we want to implement is simple. You have some proxy smart contract which just accept some message which simply it's same fields which is in event. So you can write these events, but no one library knows that this is event. So you can write it, but you can read it only when somebody would implement support for that. So it's kind of stub for now if you want events, but it's not standardized, and we are open to discussion because we have the same problem.
And this your solution requires like watching the blockchain for these transactions. Rather, I guess the advantage of Ethereum's events over that would just be like this is the way that you could do it, right, with any blockchain. But if the node could support subscription endpoints or filtering endpoints, then I think that might reduce a lot of burden. Of course, tooling could solve that problem. It doesn't have to be in the node. Yeah, feel free to reach out. I don't know if you caught my email, but I'm happy to discuss this or anything else. And I'll, if you're on the Tezos Dev Slack, I'm there.
So if Tezos node doesn't support listen, you can write your own tool which can process all block with RPC and look for some event. So it's kind of similar result, but much difficult because it's not standardized.
Yep. Yeah. That's the thing, right? It's just it would be convenient for that sort of thing to be standardized. Although I'm not the biggest fan of the way that Ethereum does that filtering, I think. But that's a different talk, I suppose, a technical minutia, I suppose. Yeah, totally viable.
Okay, any more question? Yes, one more here.
Sorry, another question. So your analyzer for Ethereum contracts, could you tell us a little bit about that and whether you have any plans to extend it to the Tezos ecosystem?
Yeah, so which analyzer, I guess, are you talking about?
You mentioned an analyzer previously, so I guess it's some kind of static analysis or...
We have a Solidity debugger. It's a trace analyzer, and we also have a Solidity decoder library. And I would love for them to support more languages and more architectures than Solidity and EVM. I can go into details if you're curious. Yeah, our debugger is a trace analyzer, so the Ethereum JS or the Ethereum node JSON RPC exposes an endpoint that gives you a list of all of the operations that the machine performs, and then the Solidity compiler outputs source mapping, which we use to translate the step instructions back to their original source locations, and then we use our decoding library, which understands the allocation strategy that Solidity uses for all of its data types, and we use that to get the values, at runtime, at the time of where you're stepping in the trace. This is a challenging piece of software to port to more than one of a thing.
Okay, thanks.
Okay, more questions? Yeah, sure. Yes, Nicola.
Oh, I was just going to say that this is something that's been on the roadmap, right? Like when we are like working on the decoder and our debugger, we've kind of looked at opportunities, but it's probably not on the next, like it wouldn't be a soon thing, right? There's a lot of groundwork that would need to be done before it's possible.
Okay. Any more questions or comments? No? So let's thank Nicola again. Thank you. Okay, so I guess it's the time to close that session and day. So I would like to thank all the speakers, whether they were present here in the room this morning and in this afternoon, and as well as those who accepted to give their presentation remotely. That was very nice from them. Thank you. I would like to thank the audience also, again, the same way, present or remote. I know we have quite a few people following us on YouTube. Those people or more people will be able to watch the movie. Either the full movie will be, I guess, available very soon. We need some time to do that, but it will be kind of cut it into pieces so that people will be able to watch individual presentations whenever they want, and that will be great. So this is hopefully the first instance of a longer sequence, I hope, of events. So I don't have any time or place to give you no breaking news, but it would be great if we could reorganize next events just like this. I would like to thank especially the people without whom nothing would have been possible. This day would have been simply impossible because it's been very complex to organize. So many people from Nomadic Labs gave help to do that, especially Emena and Oana. Emena is here, so let's give her a warm round of applause. Thank you. And also thanks to the technical team here, Benjamin Terreo and his team.